Hello, everyone. Welcome to the May 2021 Ask Me Anything edition of the Mindscape podcast. May already, 2021. It's been a long year for me. I'm sure for almost all of you also. I'm vaccinated now, though. That's good. Light at the end of the tunnel and all that. I even went into my office at Caltech where I'd actually just to do work, not to pick up mail or whatever, and which I had not done in over a year. So that's a sign of normalcy returning. Not a very optimistic sign yet. There's no one else around, basically. They're still clamping down quite heavily on the number of people who can be in the same place at the same time. So working remotely, working from home is actually still more efficient at this point. But hopefully you all are out there getting your vaccines if you can. The United States here has been doing pretty well at getting vaccines into arms, shots into arms. And so hopefully wherever you are, you can get it also, and we can get the pandemic over with. So on to the Ask Me Anything questions. As most of you know, this is a benefit for supporters on Patreon where they can ask questions. And then the answers are given out to the Patreon audience right away. And then a week or two later will be given out publicly. You can become a Patreon supporter yourself by going to patreon.com/Sean M. Carroll. It's quite affordable, $1 an episode, or whatever you want to offer. If you want to do more than that, then that's great. You don't really get many benefits. You get ad-free versions of the podcast, and you get to ask questions for the AMA. Mostly it's about just people who feel that it's nice to be able to give something back to someone who is doing something, providing content, which is a nice thing that I try to do for everybody. We've reached a point where there's too many questions, so I cannot answer all of them every month. So I try to pick and choose some and group them together. I have to say the questions this month were really good. It was very difficult to erase some of the questions. I did not answer a whole bunch of perfectly respectable, very good questions. I think that the fact that not every question gets answered now is making people raise their games, perhaps, about asking really good questions. So my apologies, as always, if I didn't answer your question. As usual, it's not mostly about the quality of the question so much as the interestingness of whatever answer I might have to give about that question. And you don't know. You don't have any way of knowing whether I have anything interesting to say about it. So don't feel bad if your question is not asked, especially if the question is of the form, tell us an interesting story about X. And I may or may not have an interesting story. That's a perfectly legitimate kind of question to ask. But don't feel bad if I don't answer. It just means I don't have any interesting stories. There you go. Sometimes my life is interesting. Sometimes it's not. We are having a different strategy this month, trying something out, a different rule, which is that the questioners, people asking questions, can put in the beginning of their question that is a priority question. And if it's a priority question, then I guarantee I will answer it. I will try to answer it anyway. And the only catch is you only get to do that once in your life. So if you have one question you really, really want answered, you can ask that in the AMA as a priority question if you're a Patreon supporter. I'll do my best to answer it. A couple people did, in fact, use that this month, so we'll see what that looks like. But anyway, lots of good questions, many good topics, whole bunch of things. Let's go. Daniel Westwater says, if UFO sightings are legitimate, which I'm not suggesting they are, do you think it's more likely they have found a way to traverse the multiverse and are actually beings that live on Earth in another multiverse rather than faster than light travel from other star systems, galaxies? So I would put here is the ranking. So I'm happy to go along with your hypothesis that UFO sightings are legitimate, even though I think they're clearly not. But I would say, number one, no FTL travel nor universe hopping in any sense. That's my most likely possibility by like 99%. Second most likely is faster than light travel. Third most likely is hopping between universes. There's no reason that you need to travel faster than the speed of light to go from one star system to another. You just have to be patient. Right? As I've said before, probably on these AMAs, we have this picture that, since a human being lasts a century or a little bit less, and it might take more than a century to get from one star system to another, you need to go faster than light to make it interesting. But that's clearly not true once you solve aging. and getting older and dying of old age, things like that, right? That is a much more tractable problem technologically than faster than light travel. Solving aging is just a biology problem. Faster than light travel is a how do you violate the laws of physics problem. So I have no trouble whatsoever in believing that advanced civilizations will either be able to live for thousands or millions of years, even as individuals, or just learn to put themselves to sleep for the course of a journey. Again, very, very tractable problems. So even if UFOs are real, I don't think you need to violate the laws of physics to do it. Of course, the laws of physics as we know them now might not be complete, might not be the final word, so maybe it's possible you can travel faster than the speed of light. There you go. I'm willing to consider that possibility. Probably it would involve some kind of warp drive kind of thing where you're taking advantage of general relativity rather than literally going faster than the speed of light. You're changing the curvature of space-time so that it appears that you're traveling faster than the speed of light. Still not very realistic in my mind, but at least something I can imagine. Hopping between universes is something I cannot even imagine, honestly. I can imagine doing it. I cannot imagine the physical mechanism that would bring it about. So I would put that last on my list of plausible things to think about as I'm constructing my Bayesian priors for this problem. Second question, I'm going to group two questions together. They're both about infinite splitting of worlds in the many worlds interpretation of quantum mechanics. The first is from Lineu Miziara, and it is labeled priority question. So as I said, this means I got to answer it, or at least got to try. And Lineu is never allowed to ask a priority question ever again. So it's good that, put yourself out there the first time. The question is, suppose I'm a working physicist waiting for an atom to decay. The probability of the atom to decay will increase as time passes. What happens according to many worlds? Does an infinite number of copies of me split as I wait, since as time passes in each fraction of a second there will be a different universe in which the atom might decay? Then another related question comes from Krzysztof Pioronsky, who says, I am almost able to imagine and believe a finite or countably infinite number of my versions in the universe. But as far as I understand, the wave function of the universe swells rather than branches. For example, a nucleus emits a neutron in radioactive decay anytime in any direction. How do you even imagine a continuum of yourselves? Could that be an indication that space-time is discrete? So both of these questions have to do with the fact that in many worlds, we tell a story where, for example, if you're measuring something discrete, like the spin of a particle that's either up or down, it's pretty simple to imagine the universe in one branch splitting into two. But when you have a continuous variable, like the position of a particle or the time at which a nucleus decayed, then it sounds like you instantly have an infinite number of universes, right? In many worlds, an unstable nucleus has, in quantum mechanics, let's put it this way. In quantum mechanics, no matter what your interpretation is, the wave function for an unstable nucleus has a part of it that says, I've not yet decayed, and another part that says, I have decayed. And that part that says, I have decayed increases with time. And so there's a probability were you to measure it that you would see the nucleus has decayed. But that part that says the nucleus has decayed is different depending on whether it decayed now or a minute ago or 10 years ago or whatever. The actual particle being emitted is doing different things. So there's a continuum of possibilities. How do you deal with that in many worlds? And I admit that it does seem harder to conceptualize, but that's no barrier to anything, right? Here's something where you have to trust the math. We'll get to this later in the AMA. Sometimes you just have to believe what the math says. It's a perfectly legitimate question to ask. How should we think about the number of worlds we're branching in, or how to coarse grain, etc., when the branching is continuous? And I think that the best answer is exactly what you would do in calculus for any other problem that goes back to, Zeno and his paradoxes, right? When you have something that is a continuum, don't talk about exactly where you are in the continuum. Talk about the probability you're between x and x plus delta x. Okay, that's a sensible thing to do. Likewise, like if you have a position just in classical mechanics on the real line between 0 and 1, what is the probability that you're at 0.3? Well, it's 0 because 0.3 is of measure 0 between 0 and 1. But you can ask, what is the probability you're between 0.3 and 0.31? Right? That's a sensible thing that will have some possibly non-zero answer. Likewise, what you think of as a world in many worlds, when there are continuous variables, you should think about the set of worlds in which the nucleus decayed between time t and t plus delta t. Okay, that's a sensible thing to think about. The number of worlds in that interval is infinite in some sense, but you can't tell the difference between them if delta t is very, very small, so you sort of group them all together. David Wallace talks about this more if you're interested in the details in his book, The Emergent Multiverse. So I think I answered both questions there. Then we have Gerard Droyvin, who also asks a priority question. And it says, in a short YouTube video called The Big Bang and Creation Myth, you suddenly hold up your hand and show, I presume this means me, although I have no idea what YouTube video is being referred to here. You suddenly hold up your hand and show the scale, maybe it doesn't mean me, I really don't remember this at all. Show the scale of our visible universe compared to the whole universe. And I think I didn't hear the word maybe when you said it is tiny, namely our visible universe. My mind made it into a compressed visible universe there between your thumb and index finger. So I thought of the Big Bang, which was tiny in its first moments, so time in there would feel different than the time we experience on Earth today because it was tiny and compressed. So for the Big Bang, inflation would not occur at top speed, as has been calculated, but since time feels different when you're compact and solid, it would have taken ages, at least if the Big Bang had eyes and a brain to sense its night sky. So the question is, does it make any sense to have thoughts like this, except that it is fun for me as a non-scientist? Is there any touch of reality to it? So I think that there's two things. Just to be super clear, a clarification first. The first thing is that I have no idea how big the universe is beyond our visible universe. We have a very good idea of how big the visible universe is. Beyond that, it might go an inch in every direction past that and then suddenly stop. That's possible. We'll find out one, microsecond later when the horizon grows a little bit. But it might grow, it might be twice the size of the visible universe. It might be 10 to the 10 to the 10 to the 10 size times the size of the visible universe. We have no idea. We can guess, and that's okay. So maybe what I should have said or tried to say, or whoever you're talking about said, is that it is completely possible that the observable universe is a tiny, tiny fraction of the entire universe. Now, this time of the Big Bang stuff, it's just not true that time flows differently or moves at a different rate near the Big Bang. Just the fact that things are dense doesn't mean that time moves any differently. Time moves at 1 second per second. You have to specify the reference frame of the clock in which is measuring the time, but in the Big Bang cosmology, there is a rest frame, right? The rest frame that we now see is the rest frame of the galaxies in the microwave background. That was true even during inflation. There was a rest frame for the inflaton field. So there was a normal, sensible way to measure time. And when we say inflation happened at whatever it was, 10 to the minus 33 seconds, that's measured in that reference frame. Sharon says, the politics of our post-World War II world has been dominated by nation-states that are sovereign unto themselves. Currently, however, we are facing crises that are global in scale, like climate change and the current pandemic we're all living through. Do you think the institution of nation-states can effectively deal with global problems without developing into a worldwide tragedy of the commons? Or do you think an international body that actually can hold them accountable would be needed? So I intentionally agreed to answer this question because I have no idea what the answer is, but it's a really interesting and important question. It's perfectly obvious that international cooperation would be a very, very good thing. I'm tempted to say a necessary thing, but at least would be very, very advisable on a whole bunch of questions, whether it's climate change, resource management, pandemics, nuclear proliferation, bioterrorism, a whole bunch of different things. There have been, when I was your age, we were living in the era when the European Union was coming together, et cetera, and there was the Iron Curtain fell, and people were optimistic that we'd be entering an age of more and more international cooperation. Things have gone backwards a little bit since then, as you may be aware of. I still think it would be a good idea. I'm not sure that something as all-encompassing as a world government would be a good idea. Governments work, or at least democratic governments work, when the people in the country, under the government, feel they have common interests, right? People in Pennsylvania are willing to pay taxes to help people in Idaho. They might not admit it, but that is the compact. That's the social contract that they're under. And I think that worldwide, here in the year 2021, people don't feel that way. about people in other countries. So, democracy is an experiment that requires buy-in. You can't impose it. And if we're thinking of a sort of democratic world government rather than just a world dictatorship, then we need to live in a world where people want to live under an umbrella, a common umbrella. And I don't think that that's true right now. I think the different nation states want to advance their own interests, right? Even here in the United States, I mean, we're not any better than anybody else. America First is very popular amongst a lot of people. It's weird, both political parties have more or less come to a consensus that we should be protectionist and put up trade barriers. The economists don't like it, but the politicians do. So I don't think we're close to that. I think that in the meantime, we're going to have a lot of attempts at getting individual agreements between different sets of countries and things like that. But that's hard to do. So I'm not really optimistic that we are quite mature enough to tackle these global problems in a sensible way. I don't know how to make it different there. That's just my feeling. And I could be wrong. This is not my area. Pablos Papageorgiou says, how do you check your ideas in theoretical physics? You mentioned writing equations. Do you then do proofs on paper, numerical models? Is there a social aspect of convincing colleagues? Basically, what happens before someone agrees to do an actual experiment? Yeah, there's a great question, actually, and you have almost put your finger on all the things that happen. The one thing I would edit is we don't do proofs in theoretical physics usually. Like sometimes you'll have an idea for something that follows straightforwardly from some assumptions in a particular physical model, and you'll prove that it's true. There are some famous examples of things like that, but mostly you sort of derive implications of your equations, right? You say like, okay, if this set of equations is true, then we should observe the following signal in a dark matter detector or something like that. So it's writing equations, pencil and paper or chalkboard or tablet or whatever you want. Certainly it's talking to people a lot, right? If you go on archive.org, arxiv.org, you can see all the theoretical physics papers and all the experimental physics papers, for that matter, that are currently being written. So you can see what they're like, right? And on the theoretical side, most papers are written by collaborations, by small collaborations. On the experimental side, they're often written by large collaborations. But people work together because they're reality checks. And also, theoretical physics is a little bit modular. Like you can write a paper together and different people can do different parts of the calculation and things like that. And then, you want to give a talk. Right? If you're invited to give a talk, you can talk about your recent work, and people in the audience will be skeptical and give you a hard time, and you try to defend yourself. All of those things actually happens. So it's very much a bottom-up kind of thing, right? It's no like Pope of theoretical physics who says, you're right, you're wrong. You work on it yourself, and you try to convince other people of it, and then you see how it goes. Submit the paper, get peer review, all that stuff. All that comes into it. Okay, I'm going to group together the next two questions because they are about universes where there's an infinite number of fluctuations long-term through the history of the universe. So first, Anonymous says, in the idle game Cookie Clicker, the goal is to get as many cookies as possible. One of the ways you can get cookies is through shipments of cookies from the Cookie Planet. In Brian Greene's book, The Hidden Reality, he claims that if space is infinite, you can not only expect to find every possible arrangement of matter out there somewhere, but there will be infinitely many copies of each possible arrangement. Is it reasonable to assume that if space is infinite, there will be an infinite number of cookie planets and similar absurdities, simply because the laws of nature don't technically forbid things like that from existing? And then another question is from Josh, who says, it's a related question, it's not exactly the same. You've said that Boltzmann brains could not come into existence because the vacuum state is never observed. What about non-vacuum quantum states that are observed, like my chair? Isn't there some tiny probability of my chair turning into a Boltzmann brain? So the reason why these are connected is because there is a very plausible cosmological scenario in which the universe expands, as it's doing now, continues to expand forever because there is vacuum energy, a cosmological constant, and within any one observable patch of that universe, the local physics is like empty space but at a certain temperature. Okay, there's a certain temperature you can associate with an accelerating universe. It's a very, very tiny temperature, 10 to the minus 30 Kelvin or something like that. I forget the exact numbers. But if you wait forever, infinitely long, so the logic goes, then you will have fluctuations into all sorts of different crazy things, including Boltzmann brains, including these configurations of materials that just have the minimum requirement to be a conscious creature of some sort. So I wrote a paper with Kim Boddy and Jason Pollock a few years ago that pointed out that scenario, as it's usually thought of, relies on a misinterpretation of quantum mechanics. It's just not true that empty space fluctuates in the vacuum, even if it's at a non-zero temperature. If you were to observe empty space, it would fluctuate. But there's no one there to observe it because you're in the vacuum. So in fact, the future vacuum state of the universe is static, there's nothing dynamically fluctuating. When we use words like fluctuations in the quantum mechanical vacuum, that's just because we're always thinking classically. We're always thinking of quantum mechanical states as kind of like statistical superpositions of different fluctuating classical states, but they're not. They're really, really different. So these Boltzmann brains that you might worry about do not fluctuate into existence in the quantum mechanical vacuum if it's truly the vacuum, if you've actually reached the vacuum state. There are other scenarios that are very similar in which you don't reach the vacuum state, and then it's a little bit different. So the question was from Josh, is there a tiny probability of your chair turning into a Boltzmann brain? Yes, there is, but it's very, very tiny. And the point is that we're going to reach the vacuum before an infinite amount of time has passed, right? So we ordinary observers, cosmologically, only exist for a finite period of time. And the probability within that finite period of time of your chair turning into a Boltzmann brain is very, very small, even if you integrate over that whole time. The reason why Boltzmann brains are talked about fluctuating into existence from the vacuum is not because it's easier to get a Boltzmann brain from the vacuum. It's because the vacuum lasts forever. So if there's even any non-zero probability, you multiply the non-zero rate of making these brains by the infinite amount of time you spend in the vacuum, and you get a non-zero, in fact, an infinite number of Boltzmann brains produced. If they were produced at all, that's what it would be. But here in the ordinary universe, you can get random crazy quantum fluctuations. They're just really, really, really unlikely. Likewise, for Anonymous's question, if space is simply infinitely big, that doesn't guarantee that everything happens somewhere. It could be. It's compatible with the fact that everything happens somewhere, but you might put restrictions on what happens. So, in other words, if space is infinitely big, it might be infinitely big, but with the feature that the same thing happens over and over again, right? It could be just like a checkerboard extended forever and ever and ever. If a checkerboard is made of black squares and white squares, you're never going to get a green square, even if you extend it infinitely far. So it depends on the specific way in which matter is arranged in an infinitely big space-time. If it's infinitely fluctuating, then you're going to get cookie planets. You're going to get all sorts of crazy things. This is all, of course, just completely speculative, things that we don't have any right to talk about from the basis of what we know empirically about the universe. But we can sensibly try to say what fits in the best with what we understand within the universe that we do see and what happens when we extrapolate it. That's an okay thing to do. Bendy Bruce says, how do you feel about the amount of investment the richest men in the world are pouring into space travel? Well, I have mixed feelings, I think, to be honest. I'm in favor of space travel. I'm in favor of both exploring space scientifically and, increasing the likelihood that human beings can live and travel into space. I think that's a good thing overall. I don't think that the concentration of wealth that we currently have in the world that gives a handful of people the right to decide how that's going to happen is a sensible way to run an establishment. I do think that I would rather just have big taxes on those people and take a lot of their money so they're still only super rich, not filthy crazy rich. And then we can collectively decide what to do with the money that we collect. Maybe help some poor people, maybe invest in science, maybe invest in education, maybe invest in space travel. I think that's just as many people have pointed out, no one becomes a multi-billionaire without help. Right? You don't become a multi-billionaire just by going out into the fields and using your muscles or by, sitting alone and using your brain. You use it because there's a system that allows you to do certain things, and talent helps, of course, but the system has to be set up for you to make a whole bunch of money. So the system should benefit. The people who are in that system should benefit as well, I think. Okay, the next two questions, I'm going to group them together, grouping a whole bunch of questions together here today. The next two questions are about Bell's theorem in different senses. So Ross Hastings says, as one of the few people in history who managed to make Einstein look like a knob, one would imagine John Stuart Bell would be a bit more famous than he is, and I can't help but wonder if the reason is because of how difficult it is to understand what he did and how he did it. I've seen videos featuring demonic clowns, etc. Being a master of wizardly explanations, I figure that if anyone can show us what it all really means, it's you. And then Joe Gravinsky says, could you explain Bell's theorem? It's the same question said in fewer words. Can you explain Bell's theorem and why it eliminates the possibility of hidden variables? Are there other reasons why hidden variables have been ruled out? So I need to undo a couple of assumptions in both of these questions. Number one, Bell's theorem did not eliminate the possibility of human variables. Number two, Bell did not make Einstein look like a knob. Einstein, everything that he said about quantum mechanics sort of in for print, right, was very, very sensible. It's not all right. Everyone makes mistakes, including Einstein, but, he was on the right track. It was Einstein who gave us the EPR experiment that led Bell to invent his inequalities, right? Without Einstein, we wouldn't have gotten there. I'll do my best in a very quick period of time because it is subtle, Bell's theorem, but I don't think that the fundamental thing is difficult to understand, honestly. The idea is simply, look, if you have a system that consists of two parts, one part is somewhere, another part is somewhere else. So they're very far apart from each other, okay? And you're going to do measurements on these two parts of the system. They could be, classically, they could be perfectly correlated. If there was some event in the past, right, that said, well, I have two balls, red ball and a blue ball, and I'm going to send one to the left and one to the right. I'm not going to look which way they go. Then obviously there's a classical correlation. Once you look at one of them, it's the red ball, then the other one is blue, etc. Right? So classically they can be perfectly correlated. But in quantum mechanics, you have this opportunity, and this is the important part. So let me just skip ahead. The point of Bell's theorem is that quantum mechanically, you can not know what answer you're going to get when you measure either one subsystem or the other, but there can be correlations between the different things. As you know from EPR, from the sort of Alice and Bob with their spins example, they can be perfectly correlated. Right? These two different things. You can have a spin that is either up or down, and the other spin is also either up or down, and you can know with 100% certainty that if you observe one up, the other will be down, and vice versa. So the tricky part of Bell's theorem is that you don't have to observe the spin in the same direction. Right? When we say you're observing the spin up or down and there's 100% correlation between them, we're imagining that you're assuming you're measuring both spins along the same axis, like the z-axis typically. Okay? And then what quantum mechanics says is if Alice measures her spin and it's up in the z direction and then Bob measures his, it would be down. But what if Bob measures his along the x-axis, right? Then it might be 50-50. Then it would be 50-50, whether it's going to be up or down. So Bell says, well, what if I just look at all the different ways that I can measure the spin, right? I mean, what would the correlations be? And what he proves is that in quantum mechanics, there will be greater correlations between those two things that you can possibly measure than you can possibly reproduce in a purely local theory. Okay, by purely local theory, we mean both what exists in the world exists only at local locations in space, right? There's a spin here, there's a spin there, and also that signals cannot travel faster than the speed of light. So you cannot touch a system in one place and instantly have it affect something somewhere else. So what Bell's theorem says is that the quantum mechanical correlations, even if they're not perfect, which they're not, if you measure a spin up and a spin x, you're not going to get perfect correlations with those. But they exist. There are some correlations, and they will be better in quantum mechanics than they possibly could be in a local theory. Now, the word local is hugely important there. That's the entire point of the theorem, is the word local in there. I did not use the words hidden variables there anywhere, right? So what Bell's theorem rules out is the possibility that Einstein did want, although he never explicitly wrote down a model, he wanted to imagine that someday we would find a hidden variable theory that was local, where both the variables and their interactions were entirely local. And Bell's theorem says you can't do that. That does not prove that Einstein was a knob, because Einstein didn't claim to do it. Einstein hoped it was possible, but he said, no, it's not really, he never actually proposed a model to do it. All he says is that quantum mechanics didn't fit his criteria for what he thought things should be, okay? So there are non-local hidden variable theories. That's what Bohmian mechanics is, or de Broglie-Bohm theory, as it's sometimes called, pilot wave theories. These are all theories where what one particle does influences another particle non-locally. And that's 100% compatible with the observation, and it's a hidden variable theory, okay? So hidden variable theories are fine, they just have to be non-local. Whether or not you count many worlds or something like that as non-local is trickier. I mean, it depends what you mean by local, depends on how you do the branching of the wave function. I don't really think it's a very interesting question, so I don't care that much. But that's the point of Bell's theorem, that you can't get in a world with unique outcomes. So in other words, with not in many worlds, but in a world where experiments give you unique outcomes, there's got to be some non-locality going on somehow. Maybe there is. There you go. Okay, the next question is, oops, I lost where I am. There we go. I'm going to group two things together once again because these are on branching of the wave function and irreversibility. So Ron Jacobson says, entanglement and branching of worlds, or collapse of the wave function if you like, sound like an irreversible event. Is it, and is this fundamentally relevant to increase in entropy and the arrow of time? And then also Suraj Rajan says, are there quantum mechanical interpretations that satisfactorily explain the arrow of time of our universe? So let me do Suraj's question first. The arrow of time of our universe is explained by the fact that entropy was low in the past, right? Entropy was low near the Big Bang. That's all you need. That explains that, and the typical understanding of what entropy is and how physics works, that explains it. So maybe what you mean is, are there quantum mechanical interpretations that explain why the early universe had low entropy? No, not as far as I know. There are quantum mechanical interpretations that have intrinsic time asymmetry in them, where the rules of physics are not the same going forward in time as backward. For example, objective collapse models are like that. You have models like what are called GRW theory and Roger Penrose's theory, where wave functions simply collapse. They really do collapse. It's not just an apparent collapse. It's a real thing. And they collapse only going forward in time. So there's a very clear, unambiguous violation of time reversal symmetry in these models. By itself, that does not explain the arrow of time in our universe, because if you started the universe in thermal equilibrium, so with a high entropy state, it would just stay high entropy even if you had collapsing wave functions. So you just have high entropy forever. That's not the arrow of time at all. No matter what happens, no matter what your theory of quantum mechanics is, you have to explain why the early universe had low entropy. And no attempt to interpret quantum mechanics does that. To get to Ron's question, yeah, the branching of the wave function is exactly an irreversible event. And why does it happen toward the future and not the past? Well, because the wave function of the universe was incredibly low entropy at early times. Now, I say that it's true, what I just said, but I shouldn't give the impression that it's clear. You know, we would like to understand much better what exactly are the features of the wave function in the early universe that give rise to the branching structure that we have, okay? So classically, the fact that the early universe needed to have low entropy to make the arrow of time is much better understood than the quantum mechanical version. I don't think it's especially hard, but it's just that, you know, the simple examples where we understand many worlds very well are laboratory-like experiments, right, where we have a clear division into system and environment, and we have decoherence in the whole thing. In the early universe, it's not even clear what the right degrees of freedom are, how to divide the world into system and environment. All that stuff becomes a little bit trickier. What do you mean by low entropy? So there's work to be done there, but basically the answer is yes. It is not an explanation of the arrow of time, but the fact that branching happens toward the future rather than the past is a consequence of the arrow of time. The arrow of time is sort of more fundamental than that fact. Okay, two more questions grouped together, and these are superficially not exactly asking about the same thing, but you'll see the relationship. Rob Butler says, as I was daydreaming last week while agitating my morning coffee, I noticed the gentle rocking of my mug had created two perfect spiral galaxies in the milk froth. Is it possible that the universe's missing gravity isn't due to a particle, but rather an extrinsic force acting on or within the universe, similar to a centrifugal or Coriolis type effect? And then Maxim Alexandrovitz says, recently after a jogging session, I've noticed something that caught my interest in my sports tracker app. It shows a diagram of every training and whenever the altitude above sea level rises, my speed drops, which is obvious. It's harder to run uphill. You slow down. But those two values, when compared together, resemble a quantum harmonic oscillator. Whenever the real part of the wave drops, the imaginary part goes up. So this is a long shot, but I can't stop thinking about the existence of additional spatial dimensions, which you mentioned as a possible result of the recent muon affair in your solo episode. Could this correlation be a possible macroscopic hint for something like that, or is it my vivid imagination? So besides the fact that these are poetic little stories being told here, the common thing about these two questions is trying to draw inspiration from a common everyday occurrence to some deep feature of the universe, which in principle is a good thing to do. Totally, respectable kind of line of reasoning to do. But here's the problem. The problem is that these systems, cream swirling into coffee or you jogging up and down the hill, these are so simple, these systems. They're very common toy models, right? They're paradigmatic. They're examples of simple kinds of physical behavior. So you expect very, very similar kinds of behavior in wildly unrelated things, right? The phenomena you're looking at here are sufficiently simple, swirls and sine waves. These are going to appear all over the place, right? In contexts that really don't have any deep fundamental true connection with each other at all. So in both cases, I'm going to say no. This is not going to work. The gravity that we use to understand dark matter is general relativity. It's very, very well tested. There's no room in our galaxy, which is very, very tiny compared to the whole universe, for something acting on it from the outside to other than just the gravity of the stuff to be causing this rotation curves to be like they are. And as you know, as I've said over and over again, let's put it that way. Maybe you don't know, but dark matter, the best evidence for dark matter comes from the cosmic microwave background, not from galaxies. So if you want to get rid of dark matter, explain the cosmic microwave background. That's what you have to do. And for the jogging up and down, it's a sine wave. There's lots of sine waves that have the property that one variable goes up and down and the other variable also goes up and down, but out of phase. Many, many, many things like that has nothing specially to do with quantum mechanics or extra dimensions in principle. That would be my answer. Okay. Sandro Stuckey says, can a photon spontaneously decay into two lower energy photons? And if so, is this process reversible? This is a good question. So the answer is no. Roughly speaking, it cannot happen. Why not? So you might think, well, if I have one photon with a certain energy, let's put it this way. If I have a particle with a certain energy and it could decay, it's allowed kinematically to decay into lower mass particles, then it does eventually. It might take some time, but eventually it will because there's sort of more room in phase space, in the space of all possible situations, for there to be multi-particle systems than single-particle systems. Roughly speaking, this is entropy increasing. There's more ways for the system to be many particles than just one particle. So if you have one photon with a certain energy, couldn't you imagine, wouldn't that logic tell you that it could decay into two photons? There's more ways to be two photons than to be one photon, right? But it doesn't work because the photon is traveling at the speed of light, basically. So not only do you have to conserve energy, you also have to conserve momentum. Right? And momentum is not just a number, it's also a direction. So if you go through the math, you might temporarily think it could happen. A single photon with a single energy E, you might say, well, that could decay into two photons, also going at the speed of light in exactly the same direction with half the energy each. Right? What's the difference between one photon with energy E and two photons with energy E over 2? And it even works out with conservation of momentum. But one problem with that, there's a technical problem with that, which is you haven't really increased the phase space of what's going on. There's zero phase space to go into because you have to get exactly the energy and momentum of both photons to line up in exactly the right way. If the photons you decay into go off back to back, then the sum of their two momenta is not moving at the speed of light. The only way that their two momenta can add up to moving the speed of light is if they move in exactly the same direction as the original photon did. So there's kind of no room for this to happen. But you might think, well, I don't know, I'm still not quite convinced. That's a little bit too persnickety for me. Well, here's the other answer. You also have to conserve angular momentum, right? Not just linear momentum. The photon is a spin 1 particle. Can one spin 1 particle decay into two spin 1 particles? Well, not unless they are orbiting each other with a total spin of 1 to get rid of the other spin 1. And that's not going to happen if they're both moving in the same direction. So once you take all of the conservation laws into account, no, one photon cannot spontaneously decay into two. If they could, we would notice. We would have seen that a long time ago. Enders Headland says, why is your website called preposterousuniverse.com? Everything you teach us is that the universe is far from preposterous. Looking forward to hearing the story behind this. Well, yes. So, spoiler alert, it's a joke. I'm just kidding with preposterousuniverse.com. It came about because back when I first got my website, I was also working on dark energy and the accelerating universe. And I wrote a paper called Dark Energy and the Preposterous Universe, because at that time, when it was still new and shiny to have dark energy and to try to explain it, we theorists were still sort of a little bit shaken with the fact that there was a non-zero cosmological constant, an acceleration to the universe. We didn't expect that. We had good arguments based on naturalness that the cosmological constant should be zero. So the point of calling the universe preposterous is not that it is preposterous, it's that it appears preposterous to us, is that there is a mismatch between our theoretical guesses as to what the universe is going to be like and what the experiments actually show us. So calling the universe preposterous is not, calling the universe names, it's calling us names. It's reminding us that we're not done yet trying to understand the universe. If the universe cannot be preposterous, the universe is the universe. It cannot be unnatural, right? The universe is by definition the most natural thing. It can appear unnatural to us, and that's our fault. That means that we need to do better. Okay, another grouped question, both about string theory. Rebecca Lashua says, is string theory a quantum field theory? Can you speak a little about the relationship between string theory and quantum field theory in general? And Marcus Kern says, I have a question about string theory. The sense I get from a layman's perspective is that its selling point is in the beauty of the theory, that it hints at a way to make known physics and also a concept of quantum gravity fall out from deeper fundamentals in a way that seems too good to be just a coincidence. The problem seems to be the ideas are fiendishly hard to prove experimentally. Could it be that this is as far as we get? Could it be that string theory is probably on the right track, but is just beyond the practical limit of what science can do in the real world? So the quantum field theory question is a very good one, because as you study physics and you learn about particles and Newtonian mechanics, and then you learn quantum mechanics, and then you learn quantum field theory, you're left with the idea that the fields are more fundamental than the particles. And in some sense, string theory seems like a step backwards from that. When you first learn string theory, it's like you're going back to the particle language, but you replaced particles with strings, okay? What happens to the fields? The fields were supposed to be progress. Are we undoing that progress? And I'm not an expert. I'm not a working string theorist. I've written a couple papers that are string theory adjacent, but I'm not a real expert in string theory, so I'm not the one to ask, but I will give you my impression here. The best we have in terms of understanding how string theory works does not come from thinking of it as a version of quantum field theory, but at some higher stringy level. There is something called string field theory. Ed Witten has written about it, and other people have also. It just seems like a cumbersome mathematical apparatus that doesn't really help us in understanding what string theory actually predicts. But we also, since the second superstring revolution in the mid-90s, the motto is string theory is not a theory of strings either, right? There are higher dimensional objects, D-branes. There are different numbers of dimensions, not only 10 dimensions, but 11 dimensions where the theory can be defined in. And in 11 dimensions, there aren't strings at all. And there's some underlying theory that presumably isn't stringy at all, that gives rise to what we know of as the famous 5 different kinds of string theory, plus the 6th 11-dimensional supergravity theory as different low-energy limits of some big underlying theory called M theory. So, and no one knows really what the fundamental, unique, most beautiful definition of M theory really is. So maybe string theory is just not worth trying to make into a string field theory because there's something even deeper that we don't know. Or maybe we haven't figured it out yet. The efforts that have been made in the direction of string field theory just haven't been up to the task yet. I don't know. Again, like this is not quite my area, so that's my impression, but you would have to ask a real expert about that. And to Marcus's question, I always object a little bit when people say, including string theorists, when they put the selling point of string theory as the beauty of the theory. Because the string theorists know, but the people who are listening them don't, that what they mean is it's a purportedly very beautiful explanation for the data that we have. It's not just beautiful, right? Who cares if something is just beautiful but has no connection to the world we observe? What makes string theories compelling is that we know we live in a world with space-time, with gauge theories for the forces of nature, with gravity and curvature, okay? And string theory gets us all of that stuff. That's what makes string theory interesting. It gets us that stuff in a particularly beautiful way if you know the theory and how it works. So it's not just the beauty that is there. And of course, it fails at getting us all the way to where we want to go. No one has yet been able to sort of explain why we live in a world that is 3 + 1 dimensional with SU3 cross SU2 cross U1 forces and things like that. That's a problem for string theory. So yes, it is possible that this could be as far as we get. I encourage you actually to listen to the podcast I did with Brian Greene, who's a working string theorist, and he was, remarkably honest about exactly that fact. He said, yeah, it's completely plausible to him that a few years from now, whatever it is, however many the number might be, string theory will be done in math departments. The ambition of string theory was absolutely to relate to the real world of experiments, to predict things that we could not otherwise explain in our accelerators and so forth. But that has not happened. Maybe it will happen tomorrow, right? Who knows? But maybe it won't. And if it doesn't, then you could absolutely see people deciding that math departments were a more appropriate place to put our string theorists, and maybe the mathematicians will think we don't need as many string theorists as the physicists do. So I think that's a very important question for string theory to face up to. We'll see what happens. We'll see where it goes. I mean, I should say that actually makes it sound overall a little bit too pessimistic. As any string theorist will tell you, correctly so, doing string theory, even though it is not latched on to experiment in any direct way, it has been an incredibly fruitful source of ideas. Ideas on black hole information, on dualities, gauge gravity dualities, things like that. So string theory is still useful to physics, even though it hasn't quite explained the standard model or anything like that quite yet. Rodrigo Nader says, about the emergence of consciousness or sentience. Do you believe that consciousness emerges from a certain condition, some neuron structure, or that it grows continuously, like that there are degrees of sentience? Would you say that every living being is a bit conscious? Well, you say every living being. I'm not panpsychist. We talked about panpsychism on the podcast with Philip Goff. Panpsychists really believe that everything is a bit conscious, right? Or at least has some mental properties in some sense. And I don't go that way myself. But I do think that consciousness is not an on or off switch either. There can be degrees of consciousness or sentience, absolutely. I think that I am more conscious than my cats. My cats are more conscious than an earthworm. Earthworm's more conscious than a bacterium. Bacterium is more conscious than a rock, okay? Now, that's probably not just because there is a single spectrum of consciousness and you just grow as you go in that direction, but there are different aspects of consciousness that come along the way. So I don't think it's either on or off, nor is it univalued, right? There's different things that you learn to do along the evolutionary tree that a bacterium it's not. So when you think about, imagining the future, I don't think a bacterium does that at all. Imagining the future might play part of a role in consciousness, and I can do it, and I can do it better than my cats, and a bacterium can't do it at all, okay? So it's not that it's doing it a little bit. So I think it's very complicated, and we don't have the complete definitions yet. We should be open-minded and develop a phenomenological theory of how those things come to be before deciding ahead of time what they are. Dan says, have you ever considered selling merchandise for the podcast? For example, the logo on a t-shirt or cup. I've considered it. Yeah, considering it is easy. Doing it is more work. I even set up a shop. I designed a t-shirt, got that far, and I made a t-shirt for myself. It's pretty awesome. I have a Mindscape t-shirt. I'm the only one who has a Mindscape t-shirt. I'm not wearing it right now, but it's a very good t-shirt. You know, if there were huge upswelling of demand for something like that, then I would do it. But, you know, it takes time. And I gotta, like I've said before in other contexts, things that take time are not things that I'm very good at doing because I have other things to do, right? I mean, you know, I got to make the podcast. I got to write books. I got to do some science. Got to get some papers out, stuff like that. So again, if there's huge demand for it, let me know. Good. 2 questions that I'm going to group together about the quantization of time. Fabian Rosdalin says, one visualization of multiple worlds is a sort of timeline splitting into multiple different timelines like a tree. But if time is also fundamentally quantum, so that not only the physical world as we know it splits into multiple worlds, but time itself splits into multiple times, does this mean that kind of visualization is misleading? And Robert Ruolana says, is time quantized? Good. So I'll take the second one first. No. As far as we know, time is just not quantized. But then again, as far as we know, space is not quantized either. You know, in quantum mechanics, so in just, well, not quantum mechanics, in good old non-relativistic quantum mechanics like you need to do to explain the hydrogen atom, or the double slit experiment, okay? When you have a bunch of particles with wave functions, et cetera, space is not quantized in those theories. Space is the location of a particle is an observable. You can measure it, and it's a continuum. You can get, in principle, any answer. So as we said before, you should think about what is the probability the particle is between point x and point x plus delta x, because it is not quantized. Now, once you get to quantum gravity, then we don't know. Maybe space is quantized, maybe not, but we don't know very much about quantum gravity at all, right? We have ideas, some of us have ideas, but we shouldn't trust those ideas quite yet. And time is even less likely to be quantized than space. You know, the Schrödinger equation is the fundamental equation of quantum mechanics, and it has time in there as a smooth continuous variable. It might not be, the Schrödinger equation might not survive into the fundamental theory of everything. There might be a better version, and there are, in fact, options for what that might be, but there's no established sense about how those options might work. The Schrödinger equation is still the best thing we have. People will often say, you know, the Planck time, which you get by combining Planck's constant and Newton's gravitational constant and the speed of light in the correct way, is somehow a quantum of time. That's just false. No one thinks that. No one who knows what's going on thinks that. It might represent a fundamental measurement precision, right? A fundamental limit to the precision that you can measure the time interval between two events or something like that. But it does not imply that time is somehow discrete in any simple way. And for Fabian's question, because the Schrödinger equation does have time in it, when we visualize the branching of worlds as, you know, one branch branches into two, and, you know, draw them going upward, let's say, on a diagram, and time is flowing upward, it is the same time. It's not multiple times. It's multiple space times, but there's a single time variable that is clicking off in the Schrödinger equation that brings both of those space times into existence. So the visualization is actually not that misleading. The only thing that could be misleading about it is if you want to imagine that the space in between the different branches of the wave function that you're visualizing somehow exists. That part is completely crazy. It's just we need to draw it somehow. It's not because there's really anything in between the different branches of the wave function. Philip Herdlichka says, I would like to ask you a question about the double slit experiment. Let's have some Neo-Copenhagen psi epistemic interpretation where the wave function, or really its square, is just a probability of finding a particle at a given place. Now, in the double slit experiment, the wave packet, which is just a probability of finding the particle, splits into two wave packets due to the slits, and it interferes with itself. The question is, if the wave packet is not real and is only a probability of finding the particle there, then the particle must have gone through only one or the other slit. So what causes the interference? If we have psi epistemic interpretations and the particle really only goes through one slit, what causes the interference? I don't know. I really don't. So I debated with myself, Philip, about whether or not I should answer this question because I don't have a good answer to it, but I can at least alert people to the existence of the question. What's going on here is that among the different possible options for one's favorite interpretation of quantum mechanics, there are options that are called psi-ontic, where the wave function psi really exists. Here it is. It's the fundamental stuff of reality, or at least part of it. So we mentioned hidden variable theories before. In the hidden variable theories, the wave function is part of reality, and the hidden variables are another part of reality. In many worlds, or in objective collapse models, it's just the wave function that is reality. In the psi epistemic models, what they're saying is that the wave function is just a tool that we use to predict the probability of certain measurement outcomes. In fact, in some versions, like in cubism, different people can assign different wave functions to exactly the same physical system because they have different amounts of knowledge, and so they know different things about the system and give it different probabilities for doing things. Now, the question you're asking is, don't we have evidence from things like the double slit experiment? Don't we have evidence that the wave function interferes with itself? Probability distributions don't interfere with themselves because they're not real. They're just, ways of measuring our ignorance. But the wave function does because it creates slits. It creates interference patterns on the other side of the double slit. So what's going on? I don't know what is going on, Philip. And I've tried to understand what psi epistemic people would say about this, but I'm not a psi epistemic person. I don't spend that much time trying to think about it because I have other things to do, right? I'm thinking about my theory that I think is more likely to be right. So you should really ask one of them. But I think that what they would say is, look, our job is to predict the outcome on the screen. Our job is not to tell you what's happening when we're not looking at it, right? The idea of a psi epistemic theory is to make predictions for the experiences of observers, not to tell some mechanistic story about what happens along the way. There may or may not be some mechanistic story to tell, I think is what they would say. But what I care about is my ability to make predictions. And so if I use some machinery to make predictions, like a wave function interfering with itself, that's fine. I'm allowed to do that. But what I care about is the predictions, are the experiences of observers. That's what I'm after at the end of the day. Again, don't trust me on this one. I'm not completely sure that's true, but I think that is what they would say. Anyway, I'm not an expert because I don't think that's a very fruitful way to go. I think that the wave function really is real, and that's the better way to go. All right, I'm going to yet again group these three questions together. You'll see why. Eric Chen says, any updates on the physics of democracy? What is the main motivation behind this project, and what do you think are the main sources of value in bringing ideas from physics to the analysis of political, economic, or other multi-agent systems? Luca Mordicini says, I first met you in the Great Courses Plus, with your courses Dark Matter and Dark Energy, the Higgs Boson, and Time. My question is, do you intend to record any new courses on that site? And Herb Bergovitz says, do you have a new teaching company course in the works? If you do, what's the topic? Teaching company and the Great Courses are the same company. So you see why I've grouped these together. They're all about questions about what I'm doing in the future. And, I think that I let my guard down a little bit here because usually I just don't say anything about what I'm working on in long-term projects for the future because, sometimes they don't pan out. They don't happen, or they don't happen at the time scale that you might want them to happen, or if they don't happen at all. But I have revealed that I am working on a book called The Physics of Democracy, and it's actually been delayed. I'm very willing to say that, and it's been delayed for a couple reasons. One is that, the major reason is that when I went into it, the Physics of Democracy, I had an outline, I had some ideas. And the idea is basically to use ideas from the physics of complex systems, multi-agent systems, emergent phenomena in multiple component aggregations of things to talk about political issues, right? And I know that some people had worked on this, obviously, but I am going to write a trade level book. So I'm going to talk about other people's interesting work to sort of let people know how a physicist would think about these things. So when I started to work on it and started to go from the brief outline I had to real work, reading other people's stuff, talking to people, what I realized is there's an enormous amount of work in this area, but it's just not labeled as such. If you look up econophysics on the internet or anywhere else, econophysics is a whole field. I mean, there are textbooks in econophysics, right? It's almost a joke, physicists going in and trying to do economics. But there are no political physics books. And so you might get the impression that no one works on it, but lots of people work on it. They just don't call it that. So it turns out that I have more work to do than I thought I would, which is fine. That's actually good news, right? I'm going to learn a whole bunch of fun things. Like half the reason why you write these books is so you can learn new fun things yourself. So it's going to take more time to do that. The other reason is we had a pandemic. Even with the original plan, I was still definitely planning on talking to a lot of people, traveling, picking people's brains and things like that, spending time at the Santa Fe Institute. We have an idea of maybe even having a workshop at Santa Fe on exactly this topic. None of that happened. None of that happened in the time scale that would have been reasonable. So we've delayed it until later. What I am hoping to do, again, I'm talking out of turn. I really shouldn't say this, but the hope, don't hold me to any of my hopes because they can go away. But the hope is to instead write the biggest ideas in the universe, right? The videos that I did last summer where I talk about the classical universe and the quantum mechanical laws of physics and field theory and renormalization, and then a little bit about complex systems and criticality and things like that, all that stuff. What I really realized while doing the videos was that it's a level of discussion that just doesn't exist out there, almost not at all. I mean, the one place maybe that tries to do something like that is Roger Penrose's book, The Road to Reality. But, it's idiosyncratically Penrosian, okay? And the idea of really doing modern physics but giving some of the equations, right? Not teaching people how to do, the product rule for derivatives or anything like that, or, complex contours in the complex plane to do integrals, none of the nitty gritty techniques you use to do mathematical analysis in theoretical physics, but enough of the conceptual framework to say, oh, look, here's a derivative, here's an integral. It's not that hard. Learning what a derivative is and learning what an integral is very easy. Learning how to calculate them is very hard. And so there's a bifurcation. There are popular level discussions where you just don't talk about that stuff, right? It's just words, no equations. Equations are considered scary. Or you do the textbook, right? You just learn everything like you're going to be a professional physicist. And what I tried to do in the videos was to say, well, there's a middle ground where I can just tell you what the equations mean without telling you how to manipulate them, without pretending you're going to grow up to be a professional physicist. I want to give you the ideas. And so I would like to develop that into a book. That is a project that is going to go first, and then Physics of Democracy second. For the great courses or the teaching company, again, yes, I would like to do another course for them, and the obvious thing to do will be quantum mechanics. I wrote a book on that, right? Something deeply hidden. So many worlds, maybe particularly, because they have a lot of courses on quantum mechanics already. If they didn't, I might just do a course on quantum mechanics in general, but they have quantum mechanics courses that are perfectly good. They don't need that. So I might just do a course on some version of what I talked about in Something Deeply Hidden. So it would be about quantum mechanics itself, but only a little bit, and then why many worlds is such an attractive version of quantum mechanics and why the foundations of quantum mechanics are important in the first place. Maybe a little bit about emergent space-time and stuff like that. Who knows? But that is the hope. All right. No more talk about future projects until I like to have them done. Otherwise I'm just putting pressure on myself. All right. What's next? Fred Alexander says, people are always searching for meaning, i.e. our purpose. From the Big Bang to decaying particles, the least common denominator seems to boil down to entropy. Is increasing entropy at the core of why all things happen in our universe? So, in a sense, yeah, actually. I'm not quite sure what answer you were expecting here, but there's a sense in which the answer to this question is yes, but let's be clear about what that sense is. So for one thing, it's crucially important to separate out, as I always try to do, time as a notion, as an idea, time, what time is it now? How long will this thing take? Stuff like that, from the arrow of time. Okay. So when I say that entropy is responsible, the fact that entropy is increasing is responsible for the arrow of time, that should not be translated in your mind to increasing entropy is responsible for time, although that happens a lot. I see people sort of paraphrasing things I say in that way, and that's just wrong, right? I mean, there's no arrow of space, but there's still space. Time exists, and it also separately has an arrow. Those are two things. So I would not say exactly the phraseology you used there is increasing entropy at the core of why all things happen. You know, we could have a universe in which time existed and things happened, but entropy didn't increase, right? It would be a very, very different universe than ours, but there would still be time and all that stuff. Okay, having said all that, having cleared that brushwork a little bit, if there are, for anything that does happen in the universe, if that thing has the property that it does not happen equally well forward or backward in time, then entropy lies behind it. That is what I would say, okay? Even the expansion of the universe only happens one way, but it could happen the other way. You could imagine running it backward, and there'd be nothing weird about that, right? So that is not to do with entropy. Whereas, you know, an ice cube melting, you don't really imagine that an ice cube would unmelt spontaneously. That's not something that you would expect to happen in the world. That does have to do with entropy. When it comes down to human beings, meaning and purpose, well, if you have a purpose, generally, I suspect, your purposes are related to things that will happen in the future. You don't have as a purpose, I would like the following thing to have happened in the past, because you have no causal leverage over the past. The past is done with, right? The future, you think you can affect by your doings here and now. And so the future is the thing about which you could have a purpose. And I think that that's a fundamental difference between the past and the future that is ultimately due to entropy. And it's because entropy is increasing that we think of the past as being fixed and the future as being influenceable. So whenever you talk about things like purpose or meaning, etc., in the background of those discussions is the fact that we treat the past and future very, very differently. And the reason why is because entropy is increasing. So the short answer is yes to your question. John Schoening says, if particle position momentum uncertainty can be explained completely classically due to matter waves and Fourier transforms, why does applying that same logic to water waves seem inconsistent, since an individual ripple in a wave of water seems to be a concrete thing as opposed to a more conceptual infinite sum? So, well, I don't know how much background the people have in general here. You've heard of the uncertainty principle, that in quantum mechanics, you cannot have a quantum state for which, if you were to measure either the position or the momentum, you can know ahead of time what either one of them will be to very, very high precision. That is not allowed in quantum mechanics. There are quantum states for which, were you to measure the position, you can predict ahead of time what answer you will get. There are quantum states for which, if you were to measure the momentum, you can predict ahead of time what you will get. There are no quantum states for which you could predict both accurately ahead of time. That's the uncertainty principle. Delta x, the uncertainty in x, times delta p is at least h bar, or h bar divided by 2, something like that. And that sounds very mysterious, and a lot of crazy talk has been expended thinking about the uncertainty principle. Once you know what a wave function is, all that craziness goes away. It has to do with Fourier transforms. And it has to do with the fact that wave functions are waves. And if you think about the wave as a wave in position, okay, so what you mean is when you have a wave function, you don't attach a wave function both to position and momentum. You draw the wave as just a function of position, and then the momentum is the wavelength, right? Or the frequency, really, of that wave that you've drawn as a function of position. So if the wave that you've drawn for position is highly peaked around just one value, then in terms of momentum, it's a sum of, as the questioner says, it's an infinite sum of many, many different momenta, and vice versa. So classical, what we call Fourier analysis, reducing a wave to its individual frequencies, makes the uncertainty principle seem almost like not even a physical option, just a mathematical necessity, right? It couldn't have been any other way. So why isn't the same thing true for something like a water wave or something like that, right? Well, there is a difference. The uncertainty principle is not classical at all. There is analogous things for classical waves. You cannot have a classical wave that is both localized in position and localized in Fourier space. The difference is that in quantum mechanics, position and momenta are both things you can observe and get specific answers for, right? So there is a relationship between that wave and the outcomes of observations in quantum mechanics that is not there in classical mechanics. In classical mechanics, if you have a water wave, you just observe the water wave. That's it. In quantum mechanics, there's a wave, but you don't observe the wave. You see either the position or the momentum observable. And so it's that relationship between the fact that you cannot localize both in position and momentum and the fact that position and momentum are both things you can observe that gives the uncertainty principle its oomph in some sense. Tim Kennedy says, how do you feel about the new political leadership in the United States? Are you pleased with the first 100 days? I think fairly pleased, yeah. Honestly, by any reasonable standard, given the previous 4 years, one has to be over the moon happy with the current political leadership in the United States. And, just so I'm very, very clear about this, and I know people can disagree with me, that's fine, but I want everyone to know what I mean when I say the words, whether or not you agree with the words. Donald Trump was just, the worst president we've ever had in the United States. And it's not because of his policies. I mean, his policies weren't that great. I could complain about his policies. It is because of the complete lack of respect for what you call democracy and the institutions of government, the corruption, the incompetence, the cult of personality, the never putting the American people first before the interests of Donald Trump and his family, completely treading over all the norms of how things happen in the democratic government, all that stuff. Still to this day, it's May, still not even accepting that he lost the election, right? That's what makes him the worst president of all time. He's still saying that, it was a cheat. And people believe him. And this has done incalculable damage to the project of democracy in the United States of America. Democracy is hard enough to get it to work when everyone believes that we are in a functioning democracy, because people disagree with each other about what the policies should be. But when you have substantial numbers of people who will just never accept the outcome of an election that doesn't go their way, the democracy can't work. And that's enormously more damaging than any particular policy that Donald Trump might have had. So it's not that, I'm Democratic or Republican. I do end up on the Democratic side most of the time. But my objections to Donald Trump weren't that he was a Republican. In fact, he wasn't a Republican, right? He was a Democrat for a long time in his life. And I like to say it this way. Imagine some horror scenario in which Donald Trump had stayed a Democrat and had run for president as a Democrat and had won the nomination to be the Democratic nominee for president. And the Republicans had nominated someone really terrible like Ted Cruz. Would I have voted for the Democrat rather than Ted Cruz, even if the Democrat were Donald Trump? And the answer is, not only in that situation would I have voted for Ted Cruz, I would have very loudly announced to everyone that I was voting for Ted Cruz, and I would have donated money to Ted Cruz's campaign against Donald Trump. Ted Cruz is a terrible person and his policies would have been terrible, but he would work within the system of our democracy much, much better than Donald Trump would have. And I know how bad he is, but compared to Donald Trump, he still would have been good. Anyway, so just the restoration of a functioning government at all, if you look at the press conferences and so forth, the press briefings, if you look at what kinds of executive orders are being signed, what kinds of legislation is moving forward, all of that stuff, it's just a back to normal feeling that is enormously helpful. In terms of actual actions on the ground, we went from one of the worst policies for dealing with the pandemic to one of the most effective vaccine distribution policies in the world. So that's pretty good. They're finally putting actual effort into restoring the economy and jobs after the effects of the pandemic. So there's plenty of things you complain about. Like, I don't agree with Joe Biden about everything or even close to everything. I think that, on certain issues like, as I already mentioned, free trade, I think that trade should be a lot freer than he's very protectionist. Immigration and the refugee crisis, he's done terrible at, so I can nitpick those things. But compared to the absolutely abysmal rock bottom presidential leadership that we had before Joe Biden, he is unimpeachably wonderful. There you go. That's what I would say about the first 100 days. Jan Smith says, what scientific discovery would disappoint you the most? So that's an interesting question. This is another one where I thought about this. Like, do I have anything interesting to say about this? Because in some sense, the respectable answer is you can't be disappointed by scientific discoveries. The world is the world, right? The universe is the universe. We don't know what it is. We're discovering it. We're not bringing it into existence. We're finding out what it is by doing science. And so every scientific discovery teaches us something new about the world. How can you be disappointed by that? Okay, but then in the real world, we're only human. I'm only human, and I would certainly prefer things to be some ways rather than other ways. But I'm not. It is hard to think because basically, if you think about it, you're rooting for certain scientific theories to come true because you think that they probably are, right? Because you sort of favor them in terms of your current tentative state of knowledge. If I don't know, if the many worlds interpretation of quantum mechanics was not true, or if general relativity was not true on large scales, that'd be really, really interesting. I don't think it's going to happen. So in some sense, I'm rooting for the theory that I spend my time thinking about, but it'd be fascinating if it weren't actually true. So the kinds of scientific discoveries that would disappoint me would be ones that somehow represented a retreat from intelligibility in the universe, right? The whole reason why science is so great is because the universe is understandable. It's hard, but we make absolute progress. And sort of features of the universe that seemed kind of inexplicable would be the worst. Now, of course, what counts as that? One of my favorite stories is with Joe Polchinski, the famous physicist who passed away a couple years ago. Back in the day, back in the mid-'90s, when I was a postdoc in Santa Barbara, and Joe and I joked about the anthropic principle, and he said, yeah, if the cosmological constant were ever discovered to be not zero, this is in like 1997, if we discovered that the cosmological constant was not zero, I would resign from physics, because the only way to explain that is with the anthropic principle, and I hate the anthropic principle. And so I said, well, okay, if that happens, can I have your office? And he said, yes. And then like a year later, they discovered the cosmological constant. And not only did I not get Joe's office, but he did not resign. And in fact, he became a big booster of the anthropic principle. He never really liked it. Like he boosted it because he's a intellectually respectable scientist. And he said, yeah, we have data. I have the cosmological constant, and the best way that I have to account for that data is with a multiverse. I don't need to like it. It's the best scientific explanation that I have to hand. So that's the kind of thing where you learn something about the universe. I'm not sure it's true. It's certainly not settled. But one could argue that the fact that we found the cosmological constant means that lowers the hope of finding a formula that once and for all predicts the cosmological constant, because the anthropic explanation becomes bigger. For me, the version of that would be something like dynamical collapse models for quantum mechanics. If you thought that wave functions really collapsed as an objective fact, and just randomly, right? Like just every so often a wave function collapses, and it only happens toward the future, not toward the past, so it violates reversibility also. That would just rub me the wrong way if it were true. I mean, again, I'd be thrilled to have learned something about the universe. This is an experimental question. We're doing experiments to look for this kind of behavior. And if it's there, I'll believe it, and I'm not giving anyone my office. But it's just so ugly in my mind. So that would disappoint me in that sense. I'm not quite sure. I would probably think of another way to think that it was really beautiful, because, again, the universe is the universe. Presumably the universe, if we understand it better, will grow to like it. Hannes Stark says, if I understand correctly, we are wondering where all the antimatter is. How do we know that some arbitrary star is made of matter and not antimatter? So the simple answer is that the universe is not as empty as you think it is, okay? If you think about galaxies that are very, very far apart, forget stars. Stars are surrounded by interstellar gas and dust, and they would constantly be running into each other. If a star were made of antimatter and the rest of the universe were made of matter, or even if they were 50-50, the matter and antimatter would constantly be hitting each other and annihilating and giving off gamma rays. That's even true if individual galaxies were matter and antimatter. There's still an intergalactic medium. It's very rarefied, it's very dilute, but the universe is big. So you can predict the amount of gamma ray radiation in the background light that would exist if galaxies were half and half, and it's way more than what we actually observe. To make things worse, the universe used to be much smaller and denser, right? And so if you say, well, now I have a galaxy or whatever that is antimatter and another one that is matter, and they're far apart, well, in the past, they used to be right on top of each other. Certainly that would be even more true with stars. So all this matter and antimatter would annihilate very, very quickly in the early universe. So we're very confident that what we see in our observable universe is almost all matter, not antimatter. Thomas Perzicki says, imagine a Star Trek-style transporter with a twist. It disassembles a person and then supposedly reassembles two identical copies of them on transporter pads 1 and 2. You have been through this transporter hundreds of times, and every time you were assembled on pad 1. How do you decide whether to accept your experience as a reasonable statistical anomaly or to suspect there is something else at play? So, to repeat, to forget this scenario correctly, you're told that when you get in the transporter, it's a 50-50 chance you go to transporter pad 1 or pad 2. But what you actually observe is you're on pad 1 every time. And so how do you judge what's going on? So I think that, this is a absolutely perfect case study for a good Bayesian analysis, right? Who cares what you're told? You have a prior belief that the transporter really does put you randomly on transporter pad 1 or transporter pad 2. And you have a prior probability that it actually always puts you on transporter pad 1. And there's a prior probability it will always put you on transporter pad 2, and another prior probability that it will alternate, and all these different things. You have a set of ideas of what the possible credences you should put with all these different theories are. Now, maybe the person who told you that it was random is very believable, and your prior probability that you always go on your prior probability that it's random is 99.99%. That's fine. But every time that you do the experiment and you keep appearing on transporter pad 1, you just run it through Bayes' formula. And Bayes' formula gives you a way of saying, given this new data, how should I change my credences? So no matter how high your credence was, that the transporter is random between pad 1 and pad 2, there will be a number of times you appear on pad 1 where you switch over from thinking it was random to thinking, you know what, I think it just sends me on pad 1 every time. But it should never go to 0 or 1 because you always have more data that you can collect in the future that might change your mind. Rob Graeber says, what is our current understanding of the initial formation of magnetic fields in the early universe? So I'm not going to give a good answer to this because I don't know what the answer is. I don't think there is a current understanding. There are current models, but I do want to sort of raise consciousness about this question because it's an interesting one. It's one that I've worked on with my PhD advisor, George Field. We're still thinking about writing a different paper about this, updating some of our older stuff. But the idea is that we have data that seems to indicate there are large-scale magnetic fields in the universe. Not huge, like the actual size of the magnetic field is quite small. I don't know exactly what the numbers are, but you can sort of measure the average amount of magnetic field between the galaxies and things like that, or even large-scale in galaxies. And so they're there, and you can ask, where do they come from? And it's not impossible to come up with scenarios to get a magnetic field. You have a bunch of charges, electric charges moving around, and we know from Maxwell's equations that once you get charges moving around, you can make magnetic fields. So for a long time now, there have been theories of batteries, like galaxies acting like batteries, winding up the magnetic fields and amplifying them. The problem is it's just an incredible nonlinear, horrible mess in magnetohydrodynamics to ask, starting with some tiny magnetic field, some seed field in the early universe, how it evolves in a situation as complex as a galaxy. In a galaxy, you have not just stars, but you have gas and dust, and some of it's ionized, some of it's not. You have supernovae going off, and they have their own magnetic fields, and you have neutron stars and black holes, and it's a mess, right? So there are people like me who don't know anything about this messy late universe stuff, but do try to answer the question, can we generate some primordial magnetic fields in the early universe with a phase transition, or something like that, that would give you a starting point to make magnetic fields in galaxies? But I don't think there's any accepted model for how that is right now. I think that knowing just the standard model of particle physics, there's no obvious way to make that happen. Maybe you need new physics. Maybe you need new scalar fields or pseudoscalar fields or something more exotic to make those magnetic fields. I think that right now the problem is just too hard and there's no consensus. Adrian says, are there any parts of physics that you never understood as well as you think you should? What is your kryptonite? So I chose to answer this question because it's a short one. All parts of physics are parts that I have never understood as well as I think I should. Even the what parts that I do, there's always more to understand, right? I don't even have any degrees in physics. I mean, that's a little bit of a cheat. Both of my degrees, undergraduate and graduate, are in astrophysics, so it's pretty close. And I took all the courses, I didn't take all the courses. I took all the courses that I thought would be relevant to my work in theoretical physics. So I took quantum mechanics and quantum field theory and general relativity and particle physics and the early universe, all those things. I took courses in those. But I could get away without, I had extra courses to take because there were required courses in the astronomy side of things. And therefore, I didn't take some of the less relevant physics courses like condensed matter physics, right? Statistical mechanics I didn't even take, which is ironic. Now I do a lot of work on statistical mechanics. But so there are absolutely aspects of those fields, especially condensed matter physics, that I don't come anywhere close to understanding as well as I would like to. Now, as well as I think I should, who's to say should? I'm actually, this is another interesting aspect of the question is, I get why, elders in physics departments want their students to get a broad-based physics education because all things being equal, it makes you a better physicist. But it's hard to predict exactly ahead of time what skills people will use in their careers. And some people just like being narrow and are very, very good at being narrow and getting their narrow thing done. And other people don't like being narrow, but would like to be broad in a different way than their elders would like them to be. Like maybe they want to be taking courses in biology or in information theory or in computer science rather than particle physics or condensed matter physics or whatever. So I don't have a list of things that everyone should know. I think that you should know the things you need to know to get ahead and tickle your curiosity. That's my philosophy of these things. Nicholas Viberg says, how could quantum field theory be compatible with the idea that the universe has a finite number of degrees of freedom, given that a field has a value at every point in space? Short answer is it's not compatible with that. If the universe has a finite number of degrees of freedom, then it is not described by a quantum field theory. It might be approximately described by a quantum field theory. So that's the hope. So for those of us who think that within our observable universe, there is a finite dimensional Hilbert space of quantum states, which you could translate into saying there are a finite number of degrees of freedom, that's exactly, well, it's not exactly, but it's very, very analogous to saying there are a finite number of atoms and molecules of air in the room that I'm in right now, but I can describe them approximately as a continuous fluid, as a gas, right? That's a good emergent approximation at low energies and large distances. Likewise, we would hope that whatever this quantum description is, that is finite dimensional, has as a low energy approximation quantum field theory, right? That's what it would have to be. But it couldn't strictly be a quantum field theory all the way down. Chris Rogers says, I live in London. Should I move to LA? Well, Chris, it depends. You'll be surprised to learn that it depends on many, many things. So I love both places. London and Los Angeles are two of my favorite cities. They're quite different. The weather is different. You may have heard about that. Los Angeles is expensive. London is crazily expensive. So Los Angeles, you get a much better house for the same amount of money than you could in London. Let's put it that way. Politics is quirky in both places. I'm not going to draw a distinction there. You know, there are different sort of quality of life issues or everyday life issues that are just different. The United States is in many ways a culture of convenience. Everyone has a car. The supermarkets sell everything. Amazon sells you everything. But it can be a little harsh, right? Healthcare, not easy to pay for sometimes. There's a sort of, get it for yourself kind of attitude in the United States that we have sometimes rather than we're all in it together. I like Los Angeles a lot. It is a wonderful city lifestyle-wise. The food is great. The weather, like I said, is great, but also there are cultural institutions that are quite good. But overall, food is also really good in London, and the culture in London is probably better overall in terms of universities, art, music, and theater, things like that. London probably has it over LA. The typical restaurant you will walk into is way better in Los Angeles than it is in London, but the best restaurants in London are probably better than the best restaurants in Los Angeles. And Los Angeles, even though it's a wonderful big city, it's spread out as a big city. You can't do in Los Angeles what is very easy to do in London or Paris or New York or Tokyo, which is go downtown and wander around, right? And something good will happen. You'll discover something good. Like in Los Angeles, there's a million great things going on, but you have to know where they are and you have to figure them out. So you either have to live here for a long time or you have to have guidance on what to do. You're also in the middle of the entertainment industry, which has its benefits. It's a whole different kind of creativity than you get in other fields. It's a unique place. No place is the center of the entertainment industry quite like Los Angeles is. So I think it's tied. Things like weather and cost of living seem very down to earth concerns, but they're important concerns. And LA wins on both of those. Food. Depends on how much you want to spend on the food. The tacos are much better in LA, but the beef Wellington is much better in London. So I like both of them. You couldn't go wrong. It depends on what you want to do for a living, which I don't know. So good luck with that. Randy Roberts says, short version of my question, is the calculation of the entropy of a physical system subjective or objective? And the answer is yes. That's a short version of the answer. Because the word entropy has different definitions. There are different ideas to which we attach the word entropy. There is a subjective definition, which is to say that entropy is somehow a measure of our ignorance of the specific details of the system. So classically, you can know that there is a system, like the air in this room, that has a microscopic state. By microscopic, we don't mean small. We just mean all of the data, the position and location, the position and velocity of every single atom and molecule in the gas, right? But we don't know it. So we have some probability distribution over what those positions and velocities are, and you can use that probability distribution to calculate an entropy. That entropy is 100% subjective. It reflects your knowledge of the system. But then there are other contexts in which entropy is perfectly objective. If you have a quantum mechanical system and you have two subsystems, and the system as a whole is in what we call a pure quantum mechanical state, it has a wave function, but the two subsystems are entangled with each other, then each one of those subsystems has an entropy given to us by John von Neumann. He has a formula for it, and that's 100% objective. That entropy has nothing to do with your knowledge of the system. It's because of the quantum mechanical state that the two entangled systems are in. And there are in-between cases, like the Boltzmann entropy, where you have a coarse graining of all the possible ways that subsystems can arrange themselves. Given the coarse graining, Boltzmann's definition of entropy is completely objective, but your choice of coarse graining in the first place is subjective, okay? So it's a little bit of a mixture. So I think that a lot of confusion around the word entropy just comes in because there's more than one definition of it, and they all overlap in appropriate regimes, but they are actually telling you very different things. Anonymous says, this is a long question I edited down a little bit, but let me see if I can get to the essence of it. With overwhelming likelihood, new particle physics would not have good practical effects for humanity. I can imagine many ways that new physics could let humanity destroy itself, but it's hard for me to come up with plausible fine-tuning so that new physics has a good effect on humanity. What do we do about this problem? So I think that the spirit of the question is, in the space of all new possible ways that I could imagine physics we haven't yet discovered, it's easier to imagine ways we could learn to hurt ourselves or would hurt ourselves inadvertently versus ways that we could help ourselves, like free energy or something like that. So what can we do about that? Well, I think that we should be honest. I don't think that you should hide the truth in any case, but I actually think that it depends what you mean by new physics. So you said new particle physics in particular. I think that it is very, very unlikely that new particle physics will have either good or bad effects for humanity other than learning more about the universe. The learning more about the universe is definitely an effect that new particle physics will have, and it's good. Okay. Whereas technological applications could be good or bad, but I don't think we're going to get any technological applications out of new particle physics. In order to make new particle physics, you need a giant particle accelerator. These are not the things that you can shrink down into the size of a phone or a wristwatch or something like that, or even a TV set. So I don't think you should look to particle physics for applications technologically. I think you should look to new particle physics for knowledge and discovery. And that's an unalloyed good in my mind. Vladimir Yoff says, if Gödel's incompleteness theorem can be applied to physics, should scientists be able to figure out which problems conceptually do not have solutions? So I'm not sure that what is meant. And it's not just you, Vladimir. There's a common sort of tendency of people to say, well, physicists try to understand everything, but Gödel's incompleteness theorem says you can't. So does that mean there's just some physics problems that have no solutions? But I think this is a case where you have to be a little bit more precise about exactly what Gödel's incompleteness theorem says. It says that if you have some formal system, right, some axiomatic mathematical system, this is not rigorously what it says, but this is casual enough to get the right answer. You cannot, the formal system cannot prove its own consistency. And the way that you demonstrate that is by saying that there are statements which basically say, I cannot be proven. Okay. So you cannot prove that. If you did prove it, then it would be inconsistent because you've proven something that says it's false. If you can't prove it, then it's true, but you can't prove it. So either there are unprovable true statements or the system is inconsistent. What in the world does that have to do with physics? I have no idea. I'm not sure what it's supposed to do with physics. That's not how physics works. Physics doesn't go around starting with axioms and proving things. Physics tries to construct models that model the world. Right? And then the world works according to that model. We don't prove theorems. That's just not what we're about. So I'm not quite sure what the exact limitation on physics is supposed to be coming from Gödel's theorem. Maybe this is my limitation. Maybe you have some more precise thing in mind, but no one who is worried about Gödel's theorem in physics has ever told me what that precise worry is. So I don't think that there's anything that Gödel's theorem should do to slow down physics in trying to understand the universe as well as it can. J.M. Autobot, probably a pseudonym, says, I'm most fascinated with your ethics and morality discussions. Although I eat plants and animals, I've been thinking more about not eating animals. You've mentioned in the past that one reason you believe it is moral to eat animals is because animals do not have the same experience that humans do about missing the life they would have experienced if they were not going to be eaten. That is true, but I struggle with the fact that I know that I shortened the experience of an animal whether it knew about its life being shortened or not. I sometimes feel bad about that. Do you have any thoughts about rationally helping me think through this one? Two things to say. One is, I'm not going to tell you should eat animals. If you feel bad about it, then don't do it. Okay. I'm a moral constructivist. I think that our ideas of right or wrong are sort of ways that we systematize our inner moral intuitions. And if your intuition is against doing something, then you can't necessarily reason your way out of it unless you have other intuitions that say you should do it and you're just trying to make them compatible with each other. So, there's nothing wrong with saying, I personally don't want to eat animals. That's a completely sensible attitude to take. But to talk about the specific reasoning that you advanced here, what you say is, you struggle with the fact that I shortened the experience of an animal, whether it knew about its life being shortened or not. So the implication seems to be that having more animals, having more experiences over the course of their lives would be good, okay? And there are absolutely moral philosophies that say that is true. You could imagine a version of utilitarianism under which that is true, where you literally take somehow you imagine that you could take the experience at each moment in the course of an animal's existence, and it's either good or bad. Hopefully it's good. Then you add them up, you do an integral over all the experiences, and you try to maximize that number, right? And I think that's something quite like what someone like Peter Singer actually does, right? You imagine there's some number called the total utility of the world, which you get by adding up all the goodness from every moment of time over every individual and maximize that number. I personally don't think that's a sensible moral system at all, right? I mean, there's various ways of arguing for that. You know, there's this formal argument called the repugnant conclusion, which argues that if you believe that kind of utilitarianism, you should believe that it is always better to have more people. No matter how miserable those people are, you can always make the world better just by increasing the number of miserable people in the world. And that doesn't seem especially moral to me. I actually think that the whole project is misguided. I don't think there's a number called utility that you can get by adding things up of different experiences at different moments of time in any way. I don't know a way to add up the experiences that a cow has and the experiences that I have. How do you compare them? That just seems impossible. Not just difficult, not like a technical problem, but like literally not a sensible thing to try to do. So I wouldn't worry about the fact that there was a life that you made shorter than otherwise. I mean, human beings as a species have changed the total diversity of life on Earth by a lot in many bad ways, okay? But how would it be different if we really tried to maximize the number of good experiences that living beings had? Whatever it would be very, 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 very different than what we are doing now. And I don't think that that's a sensible thing to try to do. So I guess all I would say is think through exactly what it is that bothers you about shortening that experience of that animal. And you may, like I said at the beginning, you may come out saying, yeah, that was bad. I don't want to do that. And that's completely okay. That's not the way that I personally feel about it. Brendan Hall said, when you arrived at Caltech, you said you were given Richard Feynman's old desk. Do you still have this desk? Do you feel bad when you spill coffee on it? And do you get to keep it after you're gone? I do have the desk. I do not feel bad when I spill coffee on it. I mean, I feel bad because I don't like to spill coffee, but they sort of every, 10 years or so, they refurbish the desk. You know, they polish it again. So it actually looks like much younger than it is. And no, I do not get to keep it after I'm gone. It will be given, once I go from Caltech, it will be given to, usually the joke that I get a lot of mileage out of, it goes to the most senior theoretical physicist who is not senior enough to get a brand new desk. So I don't know who that will be after me, but someone else will get it. Okay, I'm going to group together a bunch of questions on Laplace's demon. 3 questions on Laplace's demon. Mike Meyer says, does Laplace's demon know the exact trajectory of our lives from start to finish? Stephen Bernard says, it seems to me that if physics is deterministic, as it appears to be, then everything that exists must have been encoded in the initial state of the Big Bang, everything including all your books, the contents of the Library of Congress, etc. This baffles me. Where did all this content come from? Did it merely unfold deterministically in the fullness of time? And Jesse Rimler says, I recently listened to an episode of the BBC show In Our Time about Pierre-Simon Laplace. At one point, one of the guests said there have been numerous critiques of the idea of Laplace's demon and the deterministic model of the universe. One example is if I roll a ball up on a hill at just the right speed so that it comes to the top and is still and perfectly balanced, and then go into the future and try to see what happened in the past, I look back and this thing is still on top of the mountain. And then at some point it starts going down the mountain. There seems to be no way to predict that moment from the classical equations. Do you know what he's getting at, and does it present a challenge to the concept of Laplace's demon? So Laplace's demon, to remind you, those of you who haven't heard of it, is the idea that in classical Newtonian mechanics, it's deterministic, or at least seemingly deterministic, modulo a footnote we'll get to in a second. So in the sense that you give me the position and velocity of every particle in the universe, and Newton's laws of physics tell you what's going to happen next, okay? So Laplace said, imagine a vast intelligence that knows the position and velocity of every particle in the universe and knows all the laws of physics and has infinite calculational capacity. So to that vast intelligence, the past, present, and future are equally clear. It can figure out what will happen from the present state to the future. So for Mike Meyer's question, does Laplace's demon know the exact trajectory of our lives from start to finish? Yes, except that Laplace's demon doesn't exist. It's crucially important, by the way. Laplace's demon doesn't exist. It's a thought experiment, okay? And people get in trouble taking it a little bit too literally. It really doesn't exist. To actually model the universe effectively, you would need a Laplace's demon that was basically as big as the universe, or at least as complicated as the universe. It's not something you can, it's very, very misleading to think of it as like a dude over there who knows a lot of stuff. It's just not like that at all. To Jesse Rimler's question, yeah, there are actual subtle things about Newton's laws of physics as Newton wrote them down that make it not as deterministic as you would think. So the specific example you're talking about is called Norton's dome, after John Norton, who is still around, by the way. John Norton is a very active philosopher of science at the University of Pittsburgh, and his example is not that long ago, Norton's dome. And I talk about it, in fact, in the Biggest Ideas in the Universe videos that I mentioned before. If you want to read more about it, you can look it up there. And the idea is that, yeah, if you very, very carefully choose your physical system, then even Newton's laws are not deterministic. But the footnote there is that very, very careful is an exaggeration. It is a set of measure zero of situations you can find yourself in where there's ambiguity in what Newton's laws say. So in the space of all initial conditions for the universe, the fraction of possible initial conditions that would run into this kind of problem that you mentioned is zero. For almost all initial conditions, in the mathematically precise sense of almost all, everything's perfectly deterministic. So as a practical matter, that's not a worry. Also, Laplace's demon doesn't exist, so it's not a worry in that sense either, okay? And then to Stephen's question, so by the way, you say it seems to me that if physics is deterministic as it appears to be, I wouldn't be that quick about whether physics is deterministic or not. After all, there is quantum mechanics. Some versions of quantum mechanics are deterministic in the old-fashioned way, like the pilot wave theories, the hidden variable theories we talked about. Some versions of quantum mechanics are just not deterministic, like the objective collapse models that I mentioned. Some versions of quantum mechanics, like many worlds, are kind of deterministic, but kind of not. The wave function of the universe evolves deterministically, but the individual branches do not, okay? And I bring this up because it's relevant to your question. I mean, you have a good question that we live in an extremely complicated universe right now, extremely specific. All the information in all the books ever written or on all the hard drives or whatever, was all that implicit in the early universe? Well, it depends on your theory of quantum mechanics. We don't know whether things are deterministic. So if it's not deterministic, if wave functions truly collapse stochastically, then no. Then this information in the hard drives and the books was not there. It sort of came into existence via these stochastic jumps. If there were hidden variables, then yes. Then all the information that determined what is in all the books everywhere was there in the early universe. But, you shouldn't let that bother you. Like, where does this feeling come from that there's not enough room for all that information to be there? There could be plenty of room, right? Maybe an infinite amount of room. So I wouldn't actually be bothered about that. And then in many worlds, it's the most interesting case in some sense because the early universe could actually have had very low information content and evolved deterministically. But because the branches of the wave function differentiate themselves over time, individual branches could look like they have a high information content. And so that's kind of interesting and cool. But in that sense, the specific information about what is in the books on your branch of the wave function was not there because in the early universe, because there's no such thing as your branch of the wave function in the early universe. There was just one big branch. I hope that makes sense. Well, everything I said is true. I'm not sure if it's actually very helpful. Okay, and then to move on from Laplace's demon, there's a related set of questions about free will. And man, people love talking about free will. I don't love talking about free will. I've said this before. I think it's the most boring thing that we could be talking about. But so what I did was we got a whole bunch of questions about free will. I'm going to group them together. I'm going to give a spiel about free will, and then maybe I will get fewer questions about free will in the future. We'll see. But let me try. Let's try to read these through and give them sensible answers. So Mark Bloor says, In a block universe, if one can take a God's eye view, one will see that every conscious being is unable to predict their future, and that many of them therefore conclude that they have free will. But none of them does, in the sense that their future was set in stone when the universe was created, so does a compatibilist have any choice in taking their stance? Donald Tremblay says, the podcast with Robert Sapolsky was fascinating. Inside the framework of physicalism, where we all agree on determinism at the atomic level, which we don't, by the way, it seems to me that Dennett and Sapolsky are at opposite ends of a continuum of how much free will we have at the macro level. I rewatched a discussion you had with Sam Harris 3 years ago on this topic, at which time I'd say you were near the Dennett end. Has the needle moved for you over the past couple of years? Chris Mortlock says, I will answer all these questions. I want to get them on the table first. Chris Mortlock says, I'm interested in your opinion on individuals who commit evil acts and their free will or human accountability in engaging in such abhorrent activities. My first thought is to have hatred for these people, being the worst of the worst, but I also find myself stuck with an inner moral dilemma when I start to contemplate that these individuals are only undertaking such acts due to some kind of physical or chemical interactions in their brain or basic particle interactions outside of their control. Michael Lacey says, at the end of your podcast on rationality with Julia Galliff, she talks about self-deception as being a bad alternative for making oneself feel better. As someone who doesn't believe in libertarian free will, do you think it's okay to alleviate regret with the thought that our actions are ultimately the result of physical laws? Or, as a compatibilist, do you think that it is as much of a cop-out as self-deception? Daniela Cortese says, you said that you don't worry whether libertarian free will could be described mathematically because you don't believe in it, but isn't it important to understand regardless? If there are phenomena that can't be expressed mathematically, even in principle, isn't this a problem for a complete and sound understanding of the foundations of the universe? And finally, Flying Waffle, probably also a pseudonym, says, isn't it paradoxical that atoms don't experience choice, i.e. they just blindly follow the fundamental laws of particle physics, yet at the macro level of living organisms, brains have evolved in order to capture and model their environment in terms of probability distributions as a way to guide apparent choices? Okay, that's a lot of questions. So let me just lay out how I think about this very quickly. So there are these three different stances in free will thought, roughly speaking. One is libertarian free will, which is the idea that there's something special about human beings. We have a special spirit and ability to sort of overcome the laws of physics, right? We are a law unto ourselves. I don't believe that. Scientists generally don't believe that. Let's put libertarian free will aside for the moment. The other two options are either you're a compatibilist about free will or you're an incompatibilist, okay? Sometimes incompatibilists describe themselves as hard determinists, but that's just a mistake. That's just wrong, because whether you're a compatibilist or incompatibilist has nothing at all to do with whether the laws of physics are deterministic. I cannot possibly emphasize this enough. What matters is that there are laws. Whether those laws are deterministic or not makes zero difference to whether you're a compatibilist or an incompatibilist. You both believe that there are laws, okay? Whether you believe the fundamental laws are a pilot wave theory of quantum mechanics or a spontaneous collapse theory of quantum mechanics, one of which is deterministic and one of which is not, who cares? That doesn't affect whether you're a compatibilist or not. So don't label yourself a hard determinist. That is not the point. You would still be anti-free will if you're incompatibilist, even if the GRW theory of quantum mechanics or Penrose's theory turns out to be correct, even if determinism is not there. It's the fact that there are laws that matters. Okay. The compatibilist, what are you compatible about? You're saying that the belief in free will, that describing human beings as agents that make decisions, that make choices, is compatible with human beings being made of either neurons or elementary particles or whatever you want that obey the laws of physics. A compatibilist says you can describe the world in different ways that are compatible with each other, even though they use very different vocabularies. One way of describing the world is sort of at the microscopic level, where you're made of a bunch of particles. They're obeying the laws of physics, whatever those laws are, deterministic or indeterministic. And there's no free will there. You know, free will does not enter the Lagrangian for the standard model of particle physics, okay? No one thinks it does. And then there's another level. There's a biological level, and then there's finally a human level where you have people, okay? And the compatibilist says people make choices. This doesn't seem like a very controversial thing to say, but apparently it is. So here's one way of thinking about it. Alice and Bob are in a car. Alice is driving, Bob is navigating with his Google Maps, and they're looking for a restaurant, and Bob says, oh, turn left up here at this intersection. The restaurant will be right there once we turn left. Alice turns left, and there's no restaurant there. And Alice says, what's going on? You told me to turn left. I turned left because you told me to turn left. And Bob says, yeah, no, I knew the restaurant wasn't there, but the laws of physics said that that would be what I would say and that's what you would do, so I'm not really to blame for anything that happened. Nobody in their right mind talks that way, right? Everyone in the world who is not crazy says, Alice made a choice to turn left. Why? Because Bob told her to turn left and she trusted that Bob was going to give her the correct information, right? Bob made a choice to tell Alice something. Why? Well, I don't know. There's something perverse in Bob's mind that made him, play a little game or something like that. Literally nobody refuses to talk that way in the real world. Now, there are people who pretend to not talk that way. They will say, oh no, Alice and Bob didn't make any choices. But when it comes right down to it, these people are constantly trying to convince you to choose to not believe in free will. So you can't act that way. You can't live in the world because it's not a good description of the world at the human level to act as if human beings don't make choices. The reason why compatibilists think that it's sensible to talk about human beings as agents that make choices is because that's the best theory we have of people. And it literally is everyone's theory. There's no one who doesn't have that theory because it works. It's true. And, I did the podcast with Sam Harris a long time ago. So this is a little frustration that comes out from me, and I will vent my frustration here. And it's not just Sam Harris; it's many other people. I don't think I have ever met a incompatibilist who could correctly describe to me what compatibilists think. There's only straw compatibilists live in the mind of incompatibilists, and the incompatibilists seem to think that if they, if you really believe in the laws of physics, that they can construct a logical cage to get you to admit that we're made of particles that obey the laws of physics. But I admit that. And the discussion with Sam was incredibly frustrating because that's what he was trying to do. He was trying to say if I knew all of the laws and all of the particles and I was Laplace's demon, and he's pushing against an open door. I admit all that. If you describe the universe as microscopically in the laws of physics, then it obeys the laws of physics and there's no free will there. That's just not the point in the point of view of a compatibilist. And this is why it's very important to realize that Laplace's demon doesn't exist and none of us is anywhere close to Laplace's demon. Now, there are interesting questions to talk about that are not that question. The interesting questions are, and this gets into some of the questions here, what about the edge cases where it becomes less and less useful to describe people as agents making choices based on good reasons, right? Like what if you are a drug addict or you have some brain damage or something like that and you're under a compulsion that forces you to do something? And then I would say, indeed, it becomes less and less useful to describe that person as an agent making rational choices. And we do. We don't describe those people as robustly as agents making rational choices. So that discussion, the practical level discussion about how to treat people who suffer in different ways from an inability to be a completely rational agent, which we all do. None of us are completely rational. Like there are degrees of it. So, how do you deal with that in the real world? That's an interesting discussion to have. But this whether or not to label it free will discussion is to me the most boring thing in the world because there aren't people who don't talk about other people as choice makers in my mind. And if you are someone who believes in the laws of physics deep down, but you say, but I will, of course, in my everyday life, I will talk about people making choices, then there's a word for what you are. It's called compatibilism. That's what you are. All right, so with that in mind, let me address some of the specific questions. Mark Bloor says, does a compatibilist have any choice in being a compatibilist given that it's baked into the laws of physics? Well, if you're describing the world at the microscopic level with including the position and velocity of every particle or the entire wave function of the universe, then no. the idea of a choice doesn't enter into that picture of the universe. But, as previously mentioned, nobody does that, nor will anybody ever do that. What we actually do is describe people incompletely, with incomplete information, with incomplete knowledge of the laws that make them do their thing, as agents making choices. And at that level of description, yes, compatibilists do have choices in taking their stances. To Donald Tremblay's questions, have I moved the needle moved for me over the past couple of years? Nope. I'm willing to move my needle. Like free will, again, it's not my favorite topic. I don't care about it. People keep talking to me about it, and so I'm not that wedded to my position, but certainly I've not heard anything to make me change my position in the last couple of years. Chris Mortlock wanted to know, how should you feel about people who commit evil acts and their free will and human accountability in engaging in abhorrent activities? Well, here's where it becomes delicate. It depends on the person, right? If you have good reason to believe that there's a sense in which the person didn't have a choice, if they were, addicted or controlled or were mentally incapable of doing something else, then the feeling I would feel for them is more feeling sorry for them. If you think that the best description we have of this person is as someone who could have done otherwise, given what we know about them, not given all the laws of physics and the microscopic state of the universe, because you don't have that, given what we know about them, could they have done otherwise rationally, then you can be angry at them. I think that's perfectly legitimate. I'm angry at people all the time. I'm angry at myself all the time. Michael Lacey said, do I think it's okay to alleviate regret with the thought that our actions are ultimately the result of physical laws? No. I think that is a cop-out. That's just like self-deception, because the fact that, again, it just doesn't matter that the actions are ultimately the result of physical laws. I don't know my microstate. That's no help psychologically. Daniela Cortese said, if there are phenomena, it's about can libertarian free will be described mathematically? So I'm not exactly sure what I said. So you began the question saying you said that you don't worry whether libertarian free will could be described mathematically because I don't believe in it. There's a sense in which anything can be described mathematically. Even if a sequence of numbers is completely random, the statement that it's completely random is a mathematical statement, right? So I do think that there would be a way to describe even libertarian free will mathematically. I think what I would mean, I don't know what I was saying when you were listening to me, so maybe I just said it badly or sloppily, but I think that the point is that libertarians don't think that there are laws that give you, in some useful way, foreknowledge of how people are going to behave, even at the level of microphysics. So the incompatibilist says, yeah, there are laws that, the laws of physics, they tell you how people are going to behave. The compatibilist says the laws of physics tell you how people are going to behave if you have the microstate of the whole universe at your disposal, but you don't. At the human level, there are at best vague tendencies. You can predict probabilistically what people are going to do, but it's not that sort of microscopic precision that you have. Whereas a libertarian would say, nope, there's just nothing you can say except maybe wait for it to happen and then categorize everything mathematically as a probability distribution or as a frequency for different things happening. So yeah, I think I don't know whether libertarian free will even makes sense. That's the more honest thing that I could say. But if it did make sense, then after the fact, you could certainly summarize what people actually did. That's something that's always possible. Finally, for Flying Waffles' question, isn't it interesting that brains have evolved in order to capture and model their environment in terms of probability distributions, even though atoms don't? I don't think it's paradoxical at all. Atoms don't have a lot of internal memory, right? Atoms cannot process information in any interesting way. Atoms just don't have a lot of registers. Once you have a tremendous individual atoms, by which I mean brains are collections of many, many, many atoms, and then you have different arrangements you can put those atoms in that correspond to different images of the outside world. So because those images are incomplete, because we have incomplete information, it makes perfect sense to me that we model our environment as probability distributions, because we don't know, and we will never know, everything there is to know about the microstate of the universe. Okay, that's enough for free will, for the moment anyway. We'll see what happens next time. Moving on, Gregory Kuznick says, Dean Bonamano argued that in the absence of direct empirical evidence for closed time-like curves, we should trust our presentist intuitions. This seems to parallel the argument against many worlds. Even if we never observe any CTCs, shouldn't the fact that their existence is predicted by known solutions to Einstein's well-tested equation give us high credence in eternalism? So I don't actually think, I mean, I am an eternalist myself, but I don't think that this parallel actually works that you're suggesting, Greg, because the point is that in many worlds, the prediction of the Schrödinger equation is that our world will actually branch, that there will be branching in the future just because tiny quantum systems become entangled with their environments. Whereas someone like Dean would say, look, when you have space-time, Einstein's equation seems to govern our space-time pretty well, seems to apply to our space-time. It also has other solutions, but classically at least there is only one universe. The fact that there's an equation that has other solutions that are not like our universe doesn't matter if it's not our universe. So these other solutions with closed time-like curves, whether it's from Tipler's cylinder or Gödel's universe or the wormholes or Gott's cosmic strings, as long as they're not our universe, that doesn't actually give us any argument against presentism, would be the argument. Pete Catullus says, this is a long question, but I think it's worth it. I don't know how to shorten it. It's a cute story. I recently read a story about a man named Joseph Furtenbach, who in 1627 supposedly performed an experiment designed to show that the Earth rotates about its axis. Furtenbach fired a cannon straight up into the air and stood calmly by the muzzle as the cannonball went up into the air. He expected the motion of the rotating Earth to cause the ball to hit the ground some distance to the west of his position. As he told onlookers if he was incorrect, the ball would instead come down on his head, killing him. The story goes that the cannonball did in fact hit the ground and form a small crater to the west of the cannon, not killing him, presumably. An amusing story, but did it prove the motion of the Earth, or was Furtenbach just lucky? Unless my understanding of physics is way off, wouldn't a cannonball fired in a perfectly perpendicular direction to the surface of the Earth be expected to land in the same spot from which it is fired, barring other forces such as wind? So, Pete, I've never heard this story before, so I don't know the details of whether or not Furtenbach was just lucky, but I think you're right in the physics analysis here. You know, there's an old saying, there are many wrong ways to get the right answer, and even though the Earth is rotating, this particular analysis by Furtenbach does not seem to be correct. Like you say, if the cannon and the cannonball and everything else is moving along with the surface of the Earth, then what you would expect is when you fire the cannonball up, it will come straight down. In fact, this is the kind of reasoning that led Galileo to invent Galilean relativity around the same time in the early 1600s. In fact, Galileo, what he talks about, I forget whether he actually did this or not, but he talks about an analogous experiment on a ship. So you go on a ship and then you climb all the way up to the mast and you can drop a cannonball or something lighter. Probably you don't want to drop a cannonball onto the ship, but anyway, you drop a ball straight down. And Galileo's point was, again, I don't know whether he did it or not, but if the ship is stationary, then you should expect the ball to fall straight down. If the ship is moving at a constant velocity, you will also expect the ball to fall straight down because the ship and the ball are moving with each other. And there's no absolute frame of reference with respect to judge your velocity. It's only relative. That's the invention of relativity in some very real sense. And Galileo was right. And in fact, Galileo used this as an argument that it's okay to think that the Earth is rotating. You wouldn't notice if the Earth is rotating because all the physical experiments you do here on Earth would have the same answers as if it weren't rotating because of relativity for exactly that reason. So I don't know what Furtenbach's story was, but again, you can reason your way into the right answer for wrong reasons. In fact, Galileo did this. Galileo had a whole explanation for the tides that was completely wrong. But he used that as evidence that the Earth was rotating. So, there you go. Lots of people had wrong reasons to get the correct answer in that case. Johnny says, in your conversation with Julia Galef, you point out that most people don't revisit or question their beliefs often enough. If you turn a critical eye upon yourself, are you also guilty of this? Sure, probably. I mean, I have a whole bunch of beliefs and I like my beliefs and they fit in together into a system that reinforces itself. And of course, one should always be critical of one's beliefs, but it's hard to do so. It's, on the other hand, easy to say that I or anyone else should be critical of our own beliefs, but very hard to say which ones we should be critical of. This is a common but very bad argument when you say something that is true and your opponent says, well, do you think you're always right? Do you think you should be doubtful of your results sometimes? And you say, yeah, no, I'm not always right. I should be doubtful of my results sometimes. And they say, well, okay, you should be doubtful of it this time. That doesn't follow logically. Like maybe this particular time you're pretty darn confident. So it's easy to say you should be critical of your own beliefs. It's harder to know which of your beliefs are the ones that might turn out to be wrong. We should all try though, right? This is an aspirational kind of thing. We should try to be good Bayesians, give credences to the things that we think are unlikely but still possible. Jeff B. says, I once had a thought about the universe and I'm wondering whether it holds any truth. The idea is that all possible states of the universe coexist, and it is merely the records of other states that give the illusion of time. So this is almost the right point of view for an eternalist to believe. In fact, the reason why I liked this question is because it is giving voice to the point of view that St. Augustine had back in, I don't know, the 3rd century or whatever it was, 4th century maybe, when Augustine in his Confessions has a famous discussion of the nature of time. And one of his quotes, he's a very quotable guy, is, the past is present memory. The idea being that in his ontology, the past exists in the present moment in the form of our records of what the past actually held. Now, he didn't know about classical mechanics or Laplace's demon. These days, we can be a little bit more quantitative and rigorous about it. The entire information is conserved from moment to moment to the extent that the laws of physics are deterministic. So in some sense, the past is contained in the present moment. The one part of your proposal that I would change is you say, all possible states of the universe coexist. And this is a very typical issue that comes up when you try to be a good eternalist. An eternalist is someone who believes that every moment of time is equally real. Because at any one moment, you and I and everyone else are embedded in that moment, we have a way of talking about the world that is loaded, temporally speaking, right, with respect to time. So what you should say as a good eternalist is, all moments of time are equally real. What is very tempting to say, but is wrong, is all moments of time are equally real now, or coexisting, or simultaneously real, or real at the same time. You're giving different moments of time a little bit of existence at the same time, which is a contradiction. That's not what is going on. So I sort of halfway agree with your proposal there, Jeff. Farron Christou says, I just listened to your solo Mindscape episode on entropic gravity from September 2019 and would like to know what your thoughts are now about holography in general and on implications for locality if information is randomly encoded on the holographic boundary, as I've heard Susskind postulate. Well, so by the way, if you're not gone through the whole back catalog, there is an episode with Susskind that you can listen to and hear his own points of view of this. My points of view, my perspective hasn't changed a lot. I have the following vague idea, and this is, so here's something where I have an idea and it could be completely wrong, so my belief would change rapidly if we learned more. We had this idea of holography. Susskind and 't Hooft and others, John Preskill and others, sort of worked toward this idea in the 1990s, trying to understand black holes. And the idea that black holes have an entropy can be used to argue that the information in a black hole can be thought of as living on the horizon of the black hole or near the horizon of the black hole rather than living inside the volume of the black hole. That was later sharpened to black hole complementarity, which says that it depends on what observer you're talking about. To an observer that falls inside, the information is scattered through the volume. To an observer outside, the information looks like it's located on the boundary. And also, it became much sharper in the context of the ADS-CFT correspondence from Juan Maldacena. Maldacena points out that there's this specific example of an anti-de Sitter cosmology where there is a boundary, and the boundary looks like a space-time of one less dimension. And in fact, in certain special cases, there's a theory of physics on the boundary that is the same as, equivalent to, a theory of quantum gravity in the bulk. That's the ADS-CFT correspondence. And so that's holography because the boundary theory, which is supposed to be equivalent to the bulk theory, lives in one lower dimension. So my feeling, I said I had a feeling here, an idea that might or may not be right. My feeling is that ADS-CFT has misled us a little bit, because ADS-CFT is a wonderful example of duality, of holography, of a working model of quantum gravity, etc. It's also not the real world. We don't live in anti-de Sitter space. And it's also hard, and it's unclear whether or not it's hard because it's intrinsically hard or we human beings aren't very good at it, but it's hard in ADS-CFT to use the purported duality between the boundary and the bulk to really talk about physics that goes on very small scales inside the bulk. It's easy to talk about big cosmological questions. It's hard to talk about small scale questions, even though many people think it's in principle possible. So I think that the misleadingness, it's not that ADS-CFT is wrong in any way, but that the way that holography might work in the real world will be sufficiently different, I'm guessing, than ADS-CFT, that focusing on ADS-CFT is not helping us as much as we would like it to. It's helping us some, it's worth doing, I think it's great, all in favor of it, but I think other kinds of thought processes are going to be needed to really get holography to work in the real world, in local conditions, in black holes or whatever. So I don't think our universe has something quite as simple and direct and tangible as a holographic boundary that we would have if we lived in ADS. I think it's going to be more subtle than that. I don't know what it's going to be, so it's easy for me to say, but we'll have to wait and see. Murray Dunn says, do we know with any certainty that the net charge or angular momentum of the universe is zero? Well, no, we know very few things with any certainty about the universe. We should always be humble about those things. The statement we can make is, given the laws of physics as we understand them, in a closed universe, in a universe where space is a closed manifold, either a sphere or a torus or whatever, then the net charge and angular momentum and even the net energy will be zero. That's just a topological fact, okay? The field lines can't go anywhere, right? Like if you have an electric charge, its electrical field lines stretch out to infinity. But if you live on a torus or a sphere, infinity comes back on itself, and those field lines have to come back and go somewhere, and they can't unless the net charge is zero. If you think about a positive charge at the north pole of a sphere, if you don't want to have charges anywhere else, you're going to need to have a negative charge at the south pole of a sphere to make everything work out consistently. But what we don't know is whether or not the universe is closed. Maybe the universe is open. If the universe is open, then we can certainly have a net charge or net angular momentum, no problem. Thomas Prunty says, in this week's solo podcast, you did a lot of talking about particles and Feynman diagrams, clouds of virtual particles, etc., essentially nothing about fields. In the past, you've emphasized fields as being more fundamental. What gives? I actually, when I was planning out that solo podcast, I thought about talking in terms of fields, but then I had the thought that, number one, it would be a lot more talk, and number two, it would be distracting from what I was trying to talk about. I would basically be saying the same things, but with an extra 20-minute digression on why it's really fields, okay? But that's not the point. The point was to talk about the particular experimental results that we were trying to explain here. So what I try to say is fields are more fundamental. You're right in quantum field theory, but there's a good reason why we call it particle physics. In the regime where you have tiny vibrations in those fields, when you observe them, they look like particles. And when you calculate processes using Feynman diagrams, you're using a very particle-based language. And that's fine. Fields are more fundamental, but when the particle language is appropriate, it's appropriate. And there's no more time when particle language is appropriate than when you're doing particle physics and doing scattering experiments and calculating Feynman diagrams. So you could translate everything that I said there into talk about fields. And what I decided was that for the purposes of that discussion, it wasn't adding anything to the discussion to sort of restate exactly the same thing in the field language. There's a reason why particle physicists use Feynman diagrams all the time. They're really convenient for that kind of analysis. Anonymous says, do you have any advice for dealing with a spouse or other family member I almost said faculty member. Hopefully you have people in your family who are not faculty members. But do you have any advice for dealing with a spouse or other family member that you love dearly, but who believes wholeheartedly in things like astrology, ESP, New Age spiritualism cloaked in science, things like that? Short answer is no. It depends on the family member. Like, different people are going to be different. There are a couple of things I do think are true and are worth keeping in mind in this kind of situation. One is some people are not going to be reasoned out of their beliefs, and don't try. If you think that there's going to be someone who just isn't open to thinking about whatever their set of beliefs are, then, you're not under any obligation to bang your head against the wall and try to convince them if you know it's not going to work ahead of time. There are other people who will have such beliefs but are open-minded about them. They think that they have reasoned themselves into those beliefs in a rational way and are open to changing their minds and want to engage in discussion about it, then do that. So my point is, it depends on that individual. It also depends on you. How important is this to you that someone has the same set of beliefs about these things as you do? And I have no judgment one way or the other. Like, I totally get it. If you care about someone and love them and they're a member of your family and they have incompatible beliefs with you, and you say, you know what, that's okay. They have different beliefs. I'm just going to roll with that. We love them for other reasons. That's okay. It's also okay to say these particular beliefs are so important to me that I can't let it go, right? And you have to pick and choose where your values lie there. The final thing is there are people who might be persuadable or at least interested in talking about it, but don't want to be beaten over the head, don't want to be felt to be irrational or stupid, right? Very often, if your actual interest is not in winning some debate, but in changing someone's mind or opening them up to new possibilities, the strategy is not to bring out your biggest debating guns, right? The strategy is not to be as rational and evidence-based as you can. The strategy is to, by example, show them that they can get rid of those beliefs and still lead a happy, fulfilling life, right? Very often, and this goes back to like week 1 of the Mindscape podcast, where I interviewed Anthony Pinn, who is an atheist theologian, who's also black, and he's interested in why black people are not more atheist. And he made the point that, atheism doesn't make a good case empirically in the real world. This is not a necessary condition, but actual atheists here and now often just don't make a good case for why black people would be equally as fulfilled socially and culturally outside the church as they are inside of it. Right? So a lot of times these people reason themselves into these beliefs for reasons that are other than perfectly rational, and it's okay to reason them out of them for reasons that are other than perfectly rational. Or maybe they're rational like from a different angle, right? Like, what makes me happier? That's a perfectly rational thing to have. So think about it holistically. Think about why they believe it. Think about whether they are so devoted to it that they might change their mind, or even if they are open to talking about it at all. There's no cut and dried answer ahead of time. George Atanasov says, in your book, Something Deeply Hidden, you mentioned that the wave function of a particle spreads out in space in a roughly spherical fashion. What would be the reason for roughly? Why not perfectly spherical? Well, it depends on the details of the initial condition for the particle. So typically what I'm talking about there is, the decay of a nucleus that emits a particle. A beta decay, you emit an electron. Alpha decay, you emit a hydrogen atom. A helium nucleus. And these are things that have wave functions, and they will spread out roughly spherically. But maybe not perfectly spherically, because in fact there will be a specific wave function that is whatever is the Schrodinger equation's solution given the initial conditions. As the most obvious example, if the nucleus itself that you started with was spinning, then it's not spherically symmetric, right? A spinning nucleus has an axis around which it's spinning, and so it might emit with a wave function that is either bigger or smaller, perpendicular to that axis versus parallel to that axis. So it's just a matter of where you start that tells you where you end up. Chris Fotosh says, regarding dark matter, dark energy, new particles, the graviton, in your view, where do they fit into the standard model? Are they part of the current model as new rows or columns? Well, you've given examples here, dark matter, dark energy, new particles, the graviton. These are four very different examples. They all have very different stories to tell about them. Dark energy is most likely not a particle. It's most likely just the cosmological constant. So it's not in the standard model at all. It's just a parameter in the laws of physics, easy to add. If it is not a cosmological constant, if it's dynamical, then it could be a new particle, but a very, 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 very light particle that interacts very, very weakly with ordinary matter. Dark matter, likewise, it probably is a new particle. It interacts very weakly with ordinary matter, or we would have found it before. So I think that in some sense, there's a good way of thinking about this, and this might also be true for the muon anomalies that we talked about in the last solo podcast. Even if we extend the standard model, even if we find new things, dark matter particles, dark energy particles, or whatever, fields, it might turn out to be the case that what we currently call the standard model still has a status as a coherent sort of part of the universe, right? There's what we now call the standard model, and we'll extend it, but we'll still say that this part was the standard model, and then we have new things, right? Maybe supersymmetric particles, or excitations in extra dimensions, or relics of grand unification, but the standard model will still be the standard model. Maybe. So what I'm saying is it's not clear until we actually do it whether or not we will end up relabeling the standard model to include whatever new things we find, or we'll keep the current standard model and just say the standard model is not all of what we know in particle physics. The graviton is a special case because we know that gravity exists. We know that gravitons exist even though we've never found them. As long as you think that there is gravity and that there is quantum mechanics, something like the graviton will exist. But technically speaking, it's not in the standard model. So whatever, it's in the core theory. That's why Frank Wilczek came up with this label, the core theory, because gravity exists. You should include it. So that's gravity plus the standard model is the core theory. Adriana Sasserman says, in a scenario where there are no restrictions for civilians to go to the International Space Station, would you consider going? I'd consider it. I wouldn't be driven. I wouldn't be hyper passionate about it, to be honest. Like, it'd be fun. It'd be cool. Being out in space sounds like an awesome thing. At the same time, in the current level of technology, it is, to be fair, super dangerous. Flying into space, super dangerous. We have accidents at quite a high rate compared to what you would really like. And as cool as it would be going into space, I have a lot of cool things I still want to do here on Earth. So you have to balance that, right? You have to say, well, what is the risk that you would be willing to take? And, I think there are other people in the world who would get more out of going into space than I would, honestly. Like, I have plenty of things I want to do here on Earth. So even though I do think it would be cool, I would not do everything I can to force my way to the front of the line. How about that? Okay, I'm going to group two questions together here because they're both about the past hypothesis of low entropy in the early universe. Lothian53 says, if the early universe was high entropy, could it have had inflation or the expansion of the universe? And if we had these, wouldn't matter still clump due to gravity and then collapse into suns providing the energy to power life? Steve Pilling says, you seemed a bit doubtful about Brian Greene's paper suggesting that gravity was switched off in the early formation of the universe to account for the low entropy. This explanation seems to be quite plausible to me, and if the Higgs field was switched off, for example, this would presumably have such an effect because the particles would not gain mass from the Higgs mechanism. So both of these have to do with what we call the past hypothesis in the foundations of statistical mechanics. We know that entropy is increasing. In order to get that to happen under rules of physics that are individually, fundamentally time reversible, we need to assume an imbalance in the initial versus the final conditions of the universe. We need to assume the early universe had low entropy. That's what the past hypothesis is supposed to say. So the first question from Lothian53 is, well, what if it were high entropy? Couldn't you, and in the back of one's mind, you think, well, couldn't you have high entropy but still have the same story of inflation and expansion and clumping, et cetera? And so no, the answer is no. It depends on what you mean by high entropy. Truly high entropy, remember, what we're talking about here is a system that has gravity. Okay, so a system where space-time is curved and space-time has dynamics. That's an important part of the story. I think a lot of people get confused when they talk about gravity and entropy and cosmology by imagining we can keep the space-time fixed and mess around with what the matter is doing and call that, a new situation. But they're coupled to each other. The gravity, the curvature of space-time, and what the matter are doing both matter, as it were. So there's a result, a paper that I wrote with Aidan Chatwin-Davis, where we showed that what you mean by high entropy in a universe with a positive cosmological constant is empty space. De Sitter space. So not anti-de Sitter space, which is an empty universe with a negative cosmological constant, but de Sitter space is an empty universe with a positive cosmological constant. And so we were not the first to suggest this, but we actually were able to prove it under some assumptions. I just said an hour ago that you don't prove things, but here's an example, a counterexample, because we actually proved a little result where here are your assumptions, and we showed that there's an equivalence between what is called the cosmic no-hair theorem, which says that in the presence of a positive vacuum energy, the universe will just empty out, and you'll be left with nothing but empty space, de Sitter space, expanding forever, and the second law of thermodynamics, which says that entropy continues to increase. Eventually, you hit thermal equilibrium. Increasing entropy can be thought of as this approach to empty space. So by hypothesis, if you say, if the early universe was high entropy, it would be empty space. It would not be hot and dense and rapidly expanding. That's not what it would be, okay? So if you start with high entropy, then you're just in empty space, and you stay there forever. So you do not collapse into stars or gravity or anything like that. There's nothing around to do any of that collapsing. And to Steve's question, so Brian Greene and his collaborators had a paper which said the following thing. Again, if you imagine that you could separate out what gravity was doing from what matter is doing, then there's a sense in which the early universe, if you could ignore gravity, looks like it's high entropy. That is to say, the temperature profile of the early universe, the photons, the spectrum that we get from the cosmic microwave background, if it weren't for gravity, the spectrum looks like a black body. That's a high entropy situation. So many people have pointed this out, but the early universe looks weird in the absence of some theoretical understanding because the gravitational situation is very, very orderly and low entropy, given that the matter situation is very disorderly and high entropy, okay? Now, gravity is much more important in this situation. So overall, it's very, very low entropy, but that's a fact that we can think about trying to take advantage of. So Brian's paper tries to take advantage of that by saying, well, maybe you turn off gravity in the early universe, the matter degrees of freedom equilibrate, they go to their maximum entropy state where it looks like a black body. Then there is separately some process, magic, that turns on gravity, okay? It's not really magic, it's a scalar field or something like that, okay? Here's why that doesn't work. So one thing, footnote, this has nothing to do with the Higgs mechanism, okay? Gravity has nothing to do with the Higgs mechanism. Gravity exists whether particles have mass or don't. Gravity exists for photons. Photons have mass, but they used to dominate the energy of the universe, okay? Massiveness of particles is affected by the Higgs mechanism, completely different than gravity. Gravity is affected by Newton's constant. So when you turn off gravity in the early universe, what you're saying is Newton's constant was zero. Newton's constant of gravity in the early universe. The reason why I don't think that solves the problem is it's not robust. It's just equivalent to saying the early universe was in a very, very, very special early state. And the reason you know that is if you took our universe today and you let it collapse rather than expand, even if gravity turned off in the early universe, it wouldn't smooth out while it's collapsing, right? They cheat, in other words, by putting the universe into a very, very special initial condition. And you can show that by just reversing the problem. And so if you really want to explain robustly and without cheating the low entropy of the early universe, you need to come up with a story that works both directions in time. A story that you can say, well, you give me conditions at one moment of time, I will use the laws of physics to evolve it forward and backward, and eventually I will get the same answer. That's what Jennifer Chen and I tried to do in our 2004 paper. It's becoming like it's creeping up. People are beginning to catch on that this is a good thing to try to do. Julian Barber and his collaborators are the most famous example of people who are trying to use that kind of technique. James Cantrell says, with so much noise out there in the information sphere, how does someone who's not terribly smart go about making a smart choice in choosing what expertise to latch onto? So, James, I refuse to believe that any Patreon supporters of the Mindscape podcast are not terribly smart. You're obviously making good decisions in your life, but taking it that you must not be talking about yourself, but someone else, this is a good question. I mean, let's say, forget about being smart. Being smart is not the point, but let's say expertise. If you don't have expertise in a certain area, which all of us lack expertise in some areas, how do you go about choosing what experts to believe? There's a lot of purported experts out there, and they say incompatible things. You know, this came up a little bit in my podcast with Julia Galef. I really liked that podcast because it made me think after the fact about what we talked about a lot. And Julia, you know, one of the questions I asked her was, you want to be a good Bayesian. You want to start with some credences on different possibilities, update them on evidence. But that starting point is tricky. And especially when you're in a situation where you're not an expert and you are, like you said in your question, like you have different voices coming in and saying different things. So if you hear what might be a crackpot or what might be a brilliant idea and you don't know, you're not an expert, how do you judge, right? And so Julia actually, after the podcast, she went on Twitter and she sort of, you know, she gave an answer in real time, but then, you know, thought through it more and went on Twitter and tried to explain more. And, you know, she offered some tentative suggestions for how you would judge the credibility of a source that was making, you know, outrageous claims. You know, are they a genius or are they just a crackpot? And she got some pushback from people who said, well, all of your criteria are about the person making the claim, not the claim itself. And as she responded, like, yes, because what I'm saying is, by hypothesis, I am not an expert in judging the claims themselves. All I have to go on is the person making the claim. I think that's perfectly okay. That will be true in some cases where you just don't personally have the expertise to judge the claims for themselves. You have to think to yourself, is the person making this claim credible in my mind? And there are a number of things that go into that. Obviously, do they have a track record, right? I mean, have they made other claims in this area that have panned out? Are they recognized as an expert? Have they, whatever it takes, written papers, written books, made predictions, you know, whatever it takes to say, yes, they're not just selling you a line of goods. They know something about this. But, you know, there are people who do have a track record who then go crazy, right? That's something you also have to take in mind. I think the more interesting criterion or piece of information you can use to evaluate this question is, when they're making their claims, how do they relate those claims to other claims? In particular, how does the person making this claim talk about the arguments against their claim? So if a person says, you know, here's my claim, people will tell you I'm wrong, but they are pawns of the establishment and they're out to get me and they're dumb and whatever it is, then I'm actually much less likely to take them seriously. If people say, here are arguments why I might be wrong, and they're good arguments, I get it, I understand why you would believe it, I am now going to go through and tell you why none of these arguments are persuasive in this case. That's much more convincing to me. A person who demonstrates that they appreciate why they might be wrong is much more likely, in my mind, to be right at the end of the day. And there's other things you can think about doing, but that kind of thing, you know, you have to develop your bullshit detector. I mean, Carl Sagan had a baloney detection kit that, you know, he tried to go through, but there's no algorithm, right? You have to sort of get good at recognizing what kinds of people are credible in this kind of game. And it's hard, and you will make mistakes. We all do. I do. Jim Murphy says, I've often heard certain types of people say that humanity as a whole is sick or that we have abandoned our natural way of being. I think this is probably a bit strong, but we do seem to have a very anthropocentric way of thinking. Do you think that we need to work as a species on viewing ourselves less centrally? So I think this is a good question to sort of raise and contemplate, but I'm not sure I can give you a very persuasive, simple answer. Because, I mean, how do we judge the correct level of anthropocentrism? Like, I am a human being. I am going to think about human beings more than I am going to think about daffodils. That's just true, right? A daffodil is going to think about daffodils more than they think about human beings, I presume, unless they're being stomped on by a human being. But, it's just perfectly natural and okay to think about people and things that are in similar circumstances to you. How much to do that is a good question. So I don't know. That's a very vague answer. Sorry, I should have put more thought into this one, maybe. I guess the short answer, if I'm trying to be more direct, is I don't think it's true that we need to work as a species on viewing ourselves less centrally. I think we need to work as a species on viewing everything else more definitely, more carefully, more thoughtfully, right? More consciously. So there is the rest of the world, the rest of the universe out there, the rest of the biosphere, the rest of the species here on Earth, species maybe on other planets or whatever, and we should take them into consideration when we're doing what we do to the Earth. But I don't think that the problem is we're putting our species first. I think that individuals put themselves first, right? Individuals work for the betterment of themselves and their families and whatever, their friends, and we need cooperation, as we discussed way at the beginning of this AMA, across people around the globe to do better. Like, that's the more important thing than we should think about other species in particular. Mikko Hattainen says, how visual is your thinking? I remember you specifically mentioning visualizing things in several podcast episodes. When talking about higher dimensions in physics and math, you mentioned that visualization can only get you so far. So actually there's two things. Number one, I am actually kind of a visual thinker myself. Within mathematical approaches, or either to math or to physics, some people think visually, geometrically, roughly speaking, drawing pictures and thinking about physically tangible constructions. And other people are more equation-based, thinking more abstractly in that sense. And in that continuum, I am more on the drawing pictures side of things. I would love to someday write a paper where I prove a result or derive a result just based on pictures without any equations at all. But at the same time, I recognize that it does only take you so far. If you want to talk about a Hilbert space that is 10 to the 120 dimensional, or 10 to the 10 to the 120 dimensional, you can't visualize that. Give up. You can visualize 3 dimensions. And that's not a very representative sample of 10 to the 10 to the 120 dimensions. So then you need to use the math. So I can prefer to do things visually, and I can try to use simple examples where I can draw it to get as much intuition as I can muster. But at the end of the day, you got to trust the math. If you have a mathematical description that works where you understand it, then you should trust it where you can't visualize it until you have a good reason not to. I think that's the rule of thumb. Okay, 2 questions I'm going to group together because they're both about the Fermi paradox. Why haven't we seen intelligent aliens? Ken Wolf says, what do you think is the most likely solution to the Fermi paradox? Which is the one you would most like to be true? And David Wright says, I've always been very skeptical of media stories about any physical encounters with extraterrestrial intelligent beings based on a simple fact. Isn't it vastly more likely that we would detect extraterrestrials from their electromagnetic radiation long before we would encounter their matter? So to David's question first, I am always extremely skeptical about anyone who says, isn't it vastly more likely that aliens would do this rather than that? I don't know what aliens would do. I think we should be open-minded, other than the fact that they have very, very advanced technology, right? Presumably, like by construction, it's extraordinarily unlikely that advanced technological aliens would be more or less at our level of technology. That's just an incredible fine-tuning. It's easy for them to be millions of years further along in their development, right? No problem at all. So whatever we think about extraterrestrial technological civilizations, we should assume that they're much more technologically advanced. What that means is very hard. So no, I don't think it's necessarily true we would encounter their electromagnetic radiation long before we encounter their matter. In fact, I could come up with a perfectly plausible reason why the opposite is true. The thing about electromagnetic radiation is it zips right by you. Right? If you're an alien civilization who wants to make contact with other civilizations elsewhere in the universe, electromagnetic radiation is the dumbest thing to use because not only does the civilization you're trying to target need to be listening into you? They need to be listening into you at exactly the right time. Otherwise, the photons just go right by, or radio waves or whatever. If you really want to sort of spread through the galaxy and talk to everyone who is in other solar systems, you should send space probes. You should send matter. Why? Because you can park them there. You can send a probe to another solar system and just have it wait there for a few billion years to see if any intelligent life comes into existence. You can integrate over time in a way that you can't with electromagnetic radiation. Not to mention the fact that electromagnetic radiation being beamed out into space is just incredibly wasteful. And why would an advanced technological civilization waste all that energy? Now, I don't think that either one of these arguments is actually convincing, because I don't know what extraterrestrials would do other than the fact that they would be technologically very advanced. For Ken's question, what do I think is the most likely solution? I mean, the most likely solution is that the probability of life arising on a planet that can, in principle, support life, is small. 1 chance in 10 to the 100. There you go. There's a number that would make it very, very unlikely that there is even one other life supporting planet in our observable universe. Now, maybe life is everywhere, but multicellular life is very, very rare, or eukaryotic life or the equivalent thereof, or intelligent life or technological life. Like maybe there's lots of intelligent life everywhere in the universe, but they're all swimming in the oceans and they have flippers and they never develop opposable thumbs, so they never build spaceships, right? Any of these are possible. So I think the most likely solution is that the intelligent spacefaring civilizations just aren't there for some reason or another. It's not the only solution. And again, I think we should be humble about these things, but that's the most obvious, likely one to me. Russell Wolff says, how does entropy work with Hawking radiation? If a black hole is a maximum entropy object, does that mean that as it evaporates, its entropy decreases? No, does not mean that, because a black hole is not a maximum entropy object. This is one of those cases where you have to listen very carefully when the physicists say their words. A black hole is the maximum entropy that you can fit into a region of prescribed size. So when a black hole evaporates, it's important that not only it creates photons that leave the black hole, but those photons spread out across a huge distance. So the overall entropy of the radiation that a black hole turns into is higher than the entropy of the black hole itself. Not by a lot, by a factor of order unity, but it is bigger. But that entropy is spread out over an enormous distance. So there's no contradiction with the fact that black holes are the maximum entropy you can have in a region, because the entropy they turn into is not confined to that region. It's spread out. David Frank says, a few months back you had Avi Loeb on talking about Oumuamua. Avi shortly thereafter took a lot of criticism for his views. What's your honest view about his ideas on Oumuamua? Is he a charlatan selling snake oil, or is there some level of credibility to his ideas? So again, there's two things I want to say about this. Number one, I don't know if this came through in the podcast, but I don't care about Oumuamua. Like, that is not the point to me. What I was interested in is the general question of how should we think about taking seriously the idea of intelligent life on other planets, in some sense contacting us or being contactable or having an influence or sending something by our solar system. This particular example of Oumuamua, I don't care. I don't think we'll have any information that is going to let us decide one way or the other. So what is the point of worrying about this particular artifact? I'm very interested in, should we be on the lookout for artifacts like that? What is the probability? What is the credence that we should put into such ideas? So that's what I cared about. The other point to make is I absolutely think it's wrong to think of Avi Loeb as a charlatan selling snake oil. Number one, he's not. I know that he's not. I know Avi. I know his work. It's very off-base to think he's a charlatan selling snake oil. Number two, I am not going to have charlatans who I think are selling snake oil onto my podcast. That's just not what I am about. I do not. If I ever invite someone on the podcast, I may or may not agree with them, but I will always think that they're worth listening to and talking in good faith. Maybe I'm wrong, like maybe they have fooled me. That's always possible, right? But if I have someone on the podcast, you can take as given that I think they're worth listening to, whether or not I think that they're right. I want the audience to get something out of what they're saying. I will never have someone on the podcast just to debunk them There's plenty of that out there in the world. That's not what I'm about. I'm about listening to people who have something interesting to teach us, and I definitely think that Avi is on that side of things, whether or not he's right about this particular event. Dan Pye says, regarding your claim building on Frank Wilczek's core theory that we are overwhelmingly unlikely to discover another particle or force that is relevant to our everyday lives at the human scale, can you give an overview of how quantum field theory tells us about what we know we don't know, so to speak? I.e., how are we certain that there aren't forces affecting normal matter that simply aren't produced by any of the common interactions generated in particle accelerators? So I'll give a short answer here because I did write a paper on this very recently, the quantum field theory on which everyday life supervenes, and I've tweeted about it, so you can find it pretty easily. But you Google that, you'll find it. The point is, quantum field theory gives us rules. It's not anything goes. So the particular rule that is relevant here is one called crossing symmetry. If you have a field or a particle that can affect the fields and particles of which we are made, then it is inevitable that you can make that particle or make that field just by colliding together the particles and fields of which we are made. And that's what particle physicists do for a living. They collide together electrons and positrons, or protons and antiprotons, whatever. We smash particles together and look at what comes out. If there were any other particles that interact strongly enough with the particles we're made of that they could be relevant for human life, we would have made them already. Unless there is something dramatically wrong about quantum field theory. That's always possible, so it's not a proof of anything. Science doesn't prove things, but it means that it's telling you exactly how dramatically you have to violate the known laws of physics in order to make something like that happen. Adam Lowett says, what are your thoughts on the position held by former Mindscape guest Stuart Russell and others that artificial intelligent alignment AI safety could present a major challenge or even an existential risk to humanity in the future? So I have mixed feelings about this. You use the phrase AI alignment, AI safety, and these are two different things. AI safety, I think, is a big deal. I think we should worry about it, but it's not even AI safety. It's just complex systems risk analysis, okay? We have computers, we have technology, we have networks that no one human being can grasp the whole thing in their head, right? No one human being can grasp the whole internet and all of its details, or any sufficiently sophisticated deep learning algorithm or something like that. It does things and no human being knows exactly why it's doing what it is doing, okay? So there are obvious risks associated with that kind of thing long before you get to the point where you would call it artificially intelligent. I think that's a general question. How do you quantify risks, and how do you protect yourself against risks for complex systems which you don't fully understand? That's a very, very important question that we should put a lot of effort into. The AI alignment problem, as I understand it, and I'm not an expert, although I've had people on the program talking about it, what is being aligned here? The alignment is between the values of the AI and the values that we human beings have. That is to say, once you have an artificially intelligent system that can be said to have values in some sense, are its values our values? Are its values ones that we would hold? Does it want the same things that we want? To me, that whole discussion seems wrong-headed a little bit. I mean, there's aspects of it that make perfect sense, but it is way jumping the gun for exactly the reasons that sort of are implicit in what I just said about AI safety. Who's to say that the word values is something that even makes sense when we're talking about artificial intelligence? It seems highly anthropomorphic to me to think that we can talk about the values of an AI in more or less the same way that we can talk about the values of human beings, and therefore we can talk about aligning them together. I mean, maybe something that we would recognize as artificially intelligent has something we would recognize as values. Maybe it doesn't. Maybe they're similar to human values. Maybe they're not. Who knows? I mean, I think that there's this whole assumption that we get to choose what the values are, and that I've always worried about that assumption. I mean, if it's really artificially intelligent, can't it modify its own values in ways that we can't predict? So I just think that whole discussion is based on taking the analogy between AI and human thinking too seriously. That's not to say I don't think that AIs can't, in principle, do anything that humans can do. I'm not giving humans any special status here. But just because in principle an AI could do what a human can do doesn't mean that in practice, when you get AI, it will be human-like in any way. I presume that there are thousands, millions, who knows how many other ways to be intelligent that are different from what humans do. And maybe the AI will be one of those. And maybe it'll have values that we can recognize. Maybe it won't, right? So I think it's asking the wrong question to ask about the values of AI. What we should focus on is this more general safety problem, risk management problem. That's something that I think we should worry about. Okay, Thomas Freeman says, do you feel like you are always on when it comes to your life as a physicist? Meaning when you are watching basketball or out to dinner with your wife, could you instantly chat about the newest developments, etc.? I think it depends here. You know, when I read the question for the first time, I was thinking I'm going to say, no, I'm not always on. Because in the sense that certainly there are plenty of times in my life when I'm not thinking about physics at all, okay? When I'm thinking about basketball or poker or wine or whatever it is. But I think maybe that's not exactly what you're asking in retrospect. I mean, maybe what you're asking is, are there little subroutines running beneath the surface that are sort of physics-oriented that could be summoned up at any time or might like secretly affect how I think about basketball or poker or wine or something like that? And there, maybe, yeah, like maybe. I do think that, you know, to go back to talking about the physics of democracy, I do think that there is something called thinking like a physicist. And it's not a single thing. There are ways that physicists think. There are sort of paradigms, questions that we ask, you know, toy systems, spherical cows that we regularly refer to. Ways of analyzing complex systems, and these pop up in all sorts of different examples. You know, you don't want to be the person watching movies who constantly complains about them not obeying the laws of physics, but you know, you do notice when they don't obey the laws of physics. That is always there. So I'm certainly not always thinking about physics consciously, but maybe it is true that there are ways I am thinking about it unconsciously all the time. That I'm not quite sure, but I'm willing to believe in that. Okay, very last question comes from Brad Miller, who says, do you always feel as confident in yourself as you sound? So I guess I should thank you, Brad, for the implicit compliment that I always sound confident, or maybe it's not. You didn't actually assign a value judgment to whether or not sounding confident was good or bad. Maybe you think it's objectionable. I don't know. But I don't think here I am sounding not very confident about my level of confidence. So I don't think I'm very confident about all sorts of things. But maybe there is, and this might not be true, but maybe there is a way to sound confident just by being comfortable about quantifying your uncertainty. Right? I mean, what I do try to do, and I don't always succeed, but what I try to do is to have a pretty good handle on not just what I think is true, but the relative levels of confidence I have in different things that I believe, right? When I think that things are true, I try very hard to be clear about why I think that those are true. To be clear to myself, right? Not going badgering other people about why I think it's true, but, you know, understanding how I came to these different points of view. So, and when you sort of take that attitude about the world, that you should judge things with different credences and you should be clear as you can be about what the reasons are for having different credences in different things, then I guess you start sounding confident about it. But even if what you're saying is, oh, I have no idea, right? Many things I have no idea about, and I'm happy to say that. I'm not bothered by it. I'm not. In other words, maybe again, I'm not at all confident about this one, but maybe the appearance of not being confident comes from feeling bad when you say, I don't know. You know what I mean? So being able to say, I don't know anything about that thing, or I think this is true, but it might go away, even though you're actually expressing a great deal of uncertainty, you're doing it in a way that makes you sound confident. And maybe that is good. Maybe that is actually a virtue that you can aim for, being upfront about what you know and what you don't know, right? again, recognizing that you're always going to be wrong sometimes. You can't tell ahead of time which times. That's the problem. But you can be confident that you're going to be wrong, even if you're very confident that you have judged your credences as well as you can. So maybe that's an answer, Brad. I don't know. Not very confident in that answer. Thank you for the implicit compliment if it were indeed there. Also, I should also admit, what are you listening to me talk about? You're listening to me talk about things on my podcast. I get to choose the topics, right? And so, and I get the questions that are being asked are questions about things that I usually have talked about in the past, one way or the other. So you're not seeing a representative sample about things that I could talk about in the whole world. You're seeing me talk about things I know something about, generally, a little bit. Maybe that also gives you a misimpression of the confidence level. Anyway, something to think about. These are good questions. That was a good question. Lots of good questions. I really had fun with this AMA. See you next month. Bye-bye.